Hi everyone, welcome to Vedantu English. I'm Diksha, your chemistry master teacher. So everybody, welcome, and today we are going to do which chapter? Everyone, today we are going to do coordination chemistry, right? In your inorganic chemistry, coordination chemistry is one of the most important chapters, right? So when I talk about coordination chemistry, right? Coordination compounds, right? Here we discuss about complex compounds, right? And there are different things that we discuss. Firstly, we discuss about the name, the basic things, the IUPAC naming from where the questions are asked. Then we discuss VBT, CFT, everything we'll discuss. So first thing is, right, let me tell you about the topics that we are going to discuss. But before that, there is a very important thing, right, for all of you, that let me see how many of you comment down in the previous video, how many of you have commented. Let me see that. Let me see that. I can see TG, thank you so much, ma'am, for the lecture. Ma'am, take DNF block. Thank you, ma'am. Thank you for the session. We love your lecture. Very good. Truth about me, if chemistry classes started, I feel time to sleep, but your lecture make me boost my energy. That's awesome, right? That's awesome, Pritija. Quotations also she has written. Amazing. I'll see when I'll have time. That's such a long message. I'll see when I'll have time. I'll see that. Amazing, ma'am. You're literally a catalyst. That's so sweet of you. Thank you so much, guys, for your amazing comments, right? And the same kind of comments students are giving on our Sigma batch, right? So if you have not joined it yet, do that right now, right? So yes, now guys, let's talk about it. Those students who are thinking, ma'am, what is Sigma batch, ma'am? Sigma is crash batch, right? That has started from 10th of November, right? And in this batch, we are going to cover top high weightage topics, right, in detail, right? So this is the thing that you need for your good revision, right? At the last point, this is what you need, right? So if you talk about what we are going to discuss in today's class, right? So yes, definitely Jyotisha, we are here to help you with your JEE mains prep only, right? So today we are going to discuss about addition compounds, then important terms, then nomenclature, then Werner's theory, VBT, CFT. These are the three theories. After that, we'll discuss about colors, then metal carbonyl bonds, and then last one is isomerism. So these are the topics that we are going to cover in today's lecture, right? As you can see, every single topic I'm going to discuss in detail, right? And this is a one shot, so be ready to complete this chapter today, to revise this chapter today with me, right? Okay. Yes. Ready, everyone? Venkat, thermodynamics I'm going to take tomorrow on our Sigma crash batch. So you can definitely see, join the batch and, join the class tomorrow. And yes, right? Okay. Yes. Ma'am, duration of the class. See, this is going to be approximately 3-hour class. I'll try maybe plus minus 3-hour class. It will be maybe I'll be able to complete it within 2.5 hours or maybe 3.5 hours. I'll try to complete it within 3 hours, right? Okay. Yes. Ready, everyone? So let's start with the class. First is, let's talk about addition compounds. Addition compounds are when you add two salts, right? So compounds which are formed by combining two or more stable compounds. Two salts, when they are combined, they form addition compounds, right? And there are two types of addition compounds that we have. First type is double salt and the second type is complex salt. Double salt is the compound which dissociate into simple ions in water. Here, what you have whenever you dissociate, like you have this salt and you have this salt individually, right? And when you mix them, they make a double salt, right? In the double salt, when you dissociate them, This will be dissociated into K positive, EL3 positive, and SO42 negative. All these ions will be dissociated when you dissociate double salt. All the individual ions will be dissociated, right? But when you talk about a complex salt, if two salts they combine together to form a complex salt, they do not dissociate completely into the ions, right? If you see, when you see this dissociation, the one that is under the big square brackets will remain as it is. So here what you will have, this is, we know cross multiplication. Do you know cross multiplication? If it is ax and by, we know that by cross multiplication method, the charge on a is y positive and the charge on b is x negative, right? Because always cation is first and anion is after the cation, so that is why this is what we know from the general thing about chemistry, right? So here what we have, this will be K positive because this is 1, so it will be K positive, and here it will be plus of FeCN6, right? 4 negative. So here how much K positive? 4 K positive are there, right? And the charge is also balanced now. So that means complex ions, complex salts are not dissociated into all the ions. Here dissociation of Fe and Cn is not there because this is a complex compound. And in today's lecture we are going to discuss about these complex ions, right? One more important thing about these complex ions are that double salts are formed by equimolar ratio. Equimolar ratio. That means if this is 1 mole, this also should be 1 mole. But in the case of complex salts, they are not equimolar ratio. It is not necessary that they should be in equimolar ratio. They will not be in the equimolar ratio where we have the formation. Thank you, Pops, Manish, Sham. Yes. Anuradha, Dhanush, Silvai, Anjali, Cars Vibe, Durga, and yes, Dhanush. Okay, so beautiful names you have, right? So guys, is that clear to everyone? Yes, tell me. Thank you so much, Pops. Thanks a lot, right? So is that clear? What is the difference in double salt and complex salt? And in today's class, we are going to talk about complex salts, not the double salts, right? The examples of double salts are Mohar salt, right? I'll just write the examples here. Double salt examples are Mohar salt, okay? Potash alum, these are examples of double salt. Okay? Yes, everyone. Now let's discuss some important terms here. If you see, this is the complex compound, that which term is giving us which thing. What are the names here, right? So if you see, this is the square bracket, right? So everything that is inside the square bracket, firstly we'll understand that. So this square bracket is called as coordination sphere, right? Now if you see, here you will have a transition metal that is called as central metal atom, right? And here it will be attached to some number of molecules, right? These are called as ligands, right? And these ligands can be 4, 2, 3. There will be different number of ligands that are attached to different metals. And how many ligands, how many donor sites you have, that is called as coordination number. So coordination number means how many donor sites you have. How many donor sites you have, that will define the coordination number. So basically what we have here, that metal, central metal atom is actually electron acceptor. This accepts the electron, and ligand is electron donor. Ligand is the electron donor. Wait a minute. Yes, here. Ligand is electron donor species. Electron donor species. And one is electron acceptor, one is electron donor. So what happens? They make a coordinate bond with each other where these ligands are donating one electron pair to the metal, right? Okay, so if you see this, this one is called as counter ion. The one that is outside, that is called as counter ion, that is written over here. This is called as counter ion. This counter ion is to balance the charge that we will have inside the coordination sphere, right? Okay. Now, if you see, firstly, let's talk about coordination number. Coordination number is the number of bonds the ligands make. How many bonds the ligands are making. So, there can be 3 ligands, but the coordination number can be more than that, right? So, how do you define that thing? For that, firstly, we'll move and see what exactly is the type of ligands, right? Okay. Wait a minute. Not here, here, here. Wait a minute. Okay. So I'll just define it here only. Where should I define it? Okay. Where should we define it? I'll just define it here. So we have different types of ligands. First is bidentate ligands, then there is tridentate ligands, then there is tetradentate ligands, right? Tetradentate ligands. Then there is pentadentate ligands, pentadentate ligands, dentate ligands. Then there is hexadentate ligands, hexadentate ligands. So bidentate ligand means the one they have 2 donor sites. Okay. So 2 donor sites, like you have En, like you have En. En has 2 donation sites. Oxalato has 2 donation sites. What is En? This is quite famous. En is CH2, CH, and this is N, and this is N, right? So this is En, 1, 2, 3, 4, 1, 2, 3, 4. Okay, this is En. And what is oxalato? Oxalato is CO negative and COO negative. That is oxalato. So these are very famous bidentate ligands. Then you have tridentate ligands, the one they have 3 donating sites. Tetradentate have 4 donating sites. Pentadentates have 5 donating sites. Hexadentate, a very famous example is EDTA. I am giving you some very famous compounds. This is EDTA3 negative. This can be EDTA2 negative. This can be EDTA negative, right? So what is exactly EDTA? EDTA is nothing but if you have CH2, you have CH2, and what you have here, right, you have nitrogen, right? Same thing like ethylene diamine I am making, right? But in case of EDTA, you have CH3C, acetate here, right? So let's say in that one H you lose and will be one negative, then 2 donating sites of 2 nitrogen and 1 of oxygen. Let's say if that means it has 3 donating sites, 2 nitrogen and 1 oxygen, that is why tridentate is EDTA negative, right? If you have, let's say this is also removed and you have now 1, 2, 3, 4 donating sites, so it is tetradentate. Let's say you have, this is also removed. Now you have 1, 2, 3, 4, 5 donating sites. So pentadentate is EDTA3 negative. Now let's say you have also removed this hydrogen. Now you have EDTA4 negative. So I am telling you most important, right, ligands that you must remember. First is the structure of this one, the structure of ethylene diamine. This is oxalato, right? Then there is EDTA, that is ethylene diamine tetraacetate. Okay, ethylene diamine tetraacetate. These are some of the most famous ligands that you must know, right? Then there is another thing that is called as ambidentate ligands. Ambidentate ligands. Ambidentate ligands are which have two donating sites, but at one point only one will donate. For example, very famous is NO2 and ONO, right? Or you can have CN and NC, right? Or you can have SCN or NCS. Okay, so these are the ambidentate ligands that have two donating. See, bidentate has two donating sites, like oxalato has two donating sites, this has two donating sites, and they will donate from both the donating sites. But if you talk about ambidentate ligands, they have two donating sites, but at one point they will only donate from one donating site. Okay. EDTA, the full form is ethylene diamine tetraacetate. Ethylene diamine tetraacetate. Tetraacetate. Okay, that is EDTA. Right, everybody? Tell me, is that clear, everyone? Shiva, Vaishnavi, ma'am, can I watch these booster series without any idea of the chapters? Yes, you can watch it. I am taking it from a very basic point. Right? Yes, I have seen that, Pritija. Yes, we'll talk about chelate as well. Don't worry. Right? We'll talk about chelate as well. Right? Okay? Yes. Tell me, till here any problem? Ma'am, in EDTA, carbon is pentavalent, ma'am. Where, beta, when the carbon is pentavalent? 1, 2, 3, 4, 1, 2, 3, 4. Which carbon is pentavalent? Carbon is never pentavalent, beta. Carbon is never pentavalent, okay? Right? So, next is coordination polyhedron, right? That is clear to everybody, right? Coordination bonding also will do. We'll do that, Harshit. Don't worry. We'll do that in this series only. Don't worry, right? Firstly, tell me about this page. Is that clear? Coordination number of COC2O4. This is nothing but this is C2O4 is nothing but oxalato. Oxalato. So oxalato, if you have one oxalate has two donating sites. So 3 oxalate will have 6 donating sites, and that is why coordination number here is going to be 6. For example, they have COEN thrice. Okay. Then what will be the coordination number? It is going to be 6. Right. So these are some of the famous. Now there are also monodentate ligands. Monodentate are simple. They have only one donating site, like you have chlorine, bromine, iodine, then you have ammonia, NH3, water. All these are simple. I'll just tell you again about all these things as well, right? Acha. Now let's see this particular chart, right? Where I have given you full list of monodentate ligand, which are neutral ligands, which are charged ligands, because this is what you need to know, right? This is a table that is very, very, very important for you, right? Okay. So who wants to be blocked here? Let's see. Okay. Your wish is granted, Mr. JEE aspirant. You don't look like one. Okay. Yes. So, in the above structure, beta, where it is late, let me check. Where it is pentavalent? 1, 2, 3, 4. 1, 2, 3, 4. No. It is not pentavalent anywhere, beta. Ma'am, in the above structure CHECO, that one is seen as pentavalent. How come that is pentavalent? That is not pentavalent, beta. No, that's completely, if you're thinking about this, this is CH3, COO, O negative. It looks like this. This much basics, if I have to teach, then that is a big question mark, okay? This much basics, huh? CH3, so when it is pentavalent? When it is pentavalent? It's a 3. Oh, there you are asking. Then it will be CH2. My bad. Let me, this much, huh? You are saying this much detail. CH2. CH2, COO, negative you can write here. Right? I'll just write this here. Okay, now let's see this here. Now, if you talk about these charts here, let's talk about these charts that are quite important for you, because these charts depend, everything depends upon these charts. The full coordination chemistry depends upon these charts. Okay, let's see this. Now, if you see monodentate ligands that donates only one, that has only one donating site, right? They can be, firstly, what are the neutral monodentate ligands? Like you have ammonia, you have water, you have carbon monoxide, you have pyridine. These are monodentate, which has only one donating site, right? And they are neutral. The one they have -1 charge are like you have azide, bromide, chloride, cyanide, fluoride, hydroxide, nitrite, isonitrite, thiocyanate, isothiocyanate. These are having monodentate, but they are -1. Bidentate ligands, which has two donating sites, like you have bipyridine, that is bipyridine, which is neutral. Ethylene diamine, that I have just drawn the structure, that is neutral. Then you have, wait a minute, carbonate, that is -2 charge. Oxide is having -2 charge. Oxalate is having -2 charge. Sulfate is having -2 charge. These are having two donating sites, right? And hence they are bidentate ligands, right? Then guys, what we have, these are very important to understand, the bidentate ligands and the monodentate ligands with the charge. Okay, what is the charge on them? Everything. Now you can go through this as well. These are the anionic ligands. If you can see in the anionic ligands, can you see we have oxo, O everywhere. So what we do in the anionic ligands, O or ido is the suffix. Okay. So fluorido, chlorido, bromido, iodido, sulfato, hydroxo, cyanido, it's not oxalate, it's oxalato, carbonato, acetato, oxo, peroxo, superoxo, right? So these are the ligands that you have anionic. Then you have cationic ligands. Cationic ligands very rarely you will see. Mostly you will see anionic ligands or neutral ligands. Neutral ligands, what is the name of these ligands? Now if you see in front of negative we have OOO. In front of cationic ligand we don't have any O. We have IUM. Then in front of neutral ligands, what we have here, nothing, as it is. This is amine. H2 is not water, it's aqua. CO is carbonyl, NO is nitrosyl, O2 is dioxygen, N2 is dinitrogen. This is pyridine and this is ethylene diamine. Now, very important, in front of amine you have 2M and in diamine you have a single M here. So these are all the compounds that we have, right? These are all the ligands. You should know anionic ligands along with the charge. You should know cationic ligands along with the charge and their name. And neutral ligands, there is no charge, so their name is important. So now out of all of this, let me tell you which are the most important and most used. You have to do all of them, but I'll tell you most repeated ligands, right? So this is definitely repeated. Then you have CN is highly repeated, oxalato is repeated, acetato is repeated, oxo is also quite repeated. Then out of this cationic ligand, very rare you will say, but you should know all these things, okay? Then ammonia is very repeated, aqua, carbonyl is repeated, yes. So, and ethylene diamine. So these are very frequent in most of the compounds that we are going to discuss. You will see the one that I have marked as star, right? Okay, and here also I'll mark them. Here oxalate, which is actually oxalato, so I'll write it here. This one, ethylene diamine. Then you have cyanido, hydroxo, this one, these are also very important. Then you have, this is also important. Then you have amine, aqua, carbonyl. So these are important ligands for you, right everyone? Okay. Now let's understand, okay, these are important ligands for us. Then ma'am, what about next thing, right? Okay, let's see. Now, when metal and ligand are forming a bond, right, they are forming a bond in different structures, right? Different structures they will have. There can be octahedral structure, tetrahedral structure, square planar, trigonal bipyramidal, or square pyramidal. Different geometries they will have. And in our syllabus, we'll discuss about octahedral, tetrahedral, and square planar geometries, right? Mostly we'll discuss about that only. Not pyramidal, we'll discuss square planar geometry. Most of the cases we'll discuss these. But different polyhedrons can be there, right? Different geometries can be there. The next part is oxidation number, right? So whenever a compound is given to you, you have to calculate the oxidation number, the charge on the metal. How do you calculate? The charge would carry, the centimetal atom, what charge it would carry if all the ligands are removed along with the electron pairs that they have. So for example, you have these two complexes. I'm going to find the charge here. If you see these two complexes, guys, the one that has same type of ligands, that is called as homoleptic, and the one that has two or more than two type of ligands, that is called as heteroleptic complex, right? Now let's calculate the oxidation number. So this is x plus 0 is equals to plus 3. Now who told me that this NH3 is 0? Because I know that NH3 ammonia is not a negative ligand, it's not a positive ligand, it's a neutral ligand. So that means it is going to have 0 as the charge. So x plus 0 is equals to plus 3. So x is going to be plus 3. That means cobalt here is having plus 3 oxidation state, right? And if you see this here, this is x for cobalt. For ammonia, you have 0. And now tell me, what about chlorine? Chlorine has, it is in the category of negative ligand, it has -1 charge, right? So that is why for 1 chlorine it is -1, for 2 chlorine it is going to be -2, and you will put it overall charge is here +1. So it is x is equals to +1 plus 2, that is x is equals to +3. So here also cobalt is existing in +3 oxidation state. Okay, right? Yes. Yes, everyone, tell me. NH3 is neutral, absolutely right, absolutely right. Now let's see this question, that is the secondary valency and the number of hydrogen bonded water molecule in, wait a minute. We'll not talk about this question now, right? Because we have to study some more things. We have to study Werner theory to answer that question, okay? So now let's talk about nomenclature, right? All of that we have done. They don't directly ask you these questions, right? You know, in coordination chemistry, your base has to be very good. Now, first topic from where they ask you questions is nomenclature, right? I'll also show you some questions that they have already asked, and it's quite simple. But for that, firstly, you should know about all these tables that I have just told you about, right? Then guys, next thing is Like this is another cheat sheet where all these compounds are written, right? You can go through this. This is again in a different, whatsoever you like, you can go through that, right? Okay. Now let's see, to understand nomenclature, how do we do that, right? First thing is to understand that first you need to understand which is a counter ion, which is a coordination entity. The one that is in the bracket is coordination entity, and the one that is outside is counter ion. Here coordination entity is positive and the counter ion is negative. Here counter ion is positive, coordination entity is negative. In this case, again, coordination entity is positive and counter ion is negative, right? So always you will have cation first and then anion. Now it depends upon different formulas whether coordination entity is positive or the counter ion is positive, or both are counter ion and the coordination entity both are there as no. If positive and negative both are complexes, right? So let's see. Firstly, you need to understand why I have not written it as K2 positive. See, here you have 2, here you have 1. So this will go here, this will go here, right? And because this is cation, so it will be plus, it will be anion, so it will be minus. So that's why we have written it there, right? Then we have this one. Again, this is 1 and this is 3. So it will cross multiply here, it will cross multiply here. First is cation, then there is anion. So here it is CrEn thrice 3 positive. This is 3 positive here, right? And this is Cl negative, right? Similarly, here we will do, this is 4 and this is 3. 3 will come to this side, 4 will come to this side. This is positive, this is negative. So this is Fe3 positive and this is FeCN6 4 negative, and that is your answer. Last is you have this as the coordination sphere. This is 1 and this is 2. It will go to this side, it will go to this side. This is positive and this is negative. So this is PtCl2En twice 2 positive and this is NO3 negative. Okay. Now if you see how many numbers you have here. This is 2, so this is 2K positive. This is 3, so this is 3Cl negative. This is 4, so this is 4. And this is 3 here, so this will be 3. Right? This overall bracket is 1, so it is 1 here. And here it is 2, so it will be 2 here. Okay? So that's how you do dissociation. This one is important to form the formula and all these things. Okay? Tell me. We'll discuss about that. We'll discuss about that. Wait a minute, right? Wait a minute. Now, mononuclear coordination complexes. The cation is named first in both positively and negatively charged. Now, let's understand how nomenclature is done, right? First is the cation is named first in both positively and negatively charged species. Firstly cation, then there will be an ion, right? Ligands are named in alphabetical order before the name of the central metal ion. Firstly, you will write ligands and then you will write central metal atom. And ligands are also written in alphabetical orders. Names of the anionic ligands will end with O, and those of neutral cationic ligands are same except aqua for water, amine for NH3, carbonyl for CO, and nitrosyl for NO, right? While writing the formula, these are enclosed in brackets, right? When you write the formula, they are enclosed in brackets, right? Okay. Prefixes mono, di, tri are used to indicate number of individual ligands in the coordination entity. But if in the name of ligand itself you have bi, tri, tetra, for example, you have ethylene, diamine. So this is a ligand. In the name of the ligand itself, you have di. So let's say you have in the question, you have En thrice, right? So you can't write it triethylene diamine. That would be wrong. You will write it as tri means tris. You will write it as tris. So whenever in the ligand itself you have di, tri, tetra, then to represent the number of ligands you will use prefixes as bis, tris, Tetra kiss, penta kiss, these. Okay. Oxidation states are calculated and written in Roman numeral, right? Then if the complex ion is a cation, this is very important, then nothing will change. But if the metal ion same as element, for example, CO in a complex cation is called as cobalt, Pt is called as platinum. If the complex ion is anion, this is very important. Let's say you have K positive, let's say you have a formula K for something and this is a coordination compound. So complex entity is anion here. In that case, the central metal will be named differently. Here cobalt will be cobaltate, silver will be argentate, iron will be ferrate, nickel will be nickelate. So you will have 8, suffix 8 in the end, right? Okay. So always remember, silver is converted to not silverate, it is converted to argentate. Okay, that is important. Cobaltate, right? The neutral complex molecule is named similar to that of complex cation, right? Okay. Now let's see some of the examples where we can apply this particular concept that we have just discussed, right? Okay. Yes. So let's see this. What you're asking, Sai Priya, on chapter thermodynamic, please, ma'am. Okay, Sai Priya, I'll do that. I'll do that. Ligands lone pairs don't act as, ma'am. Why are few ligands with lone pairs don't act as? There are so many different things that are important in donation, right? So that's why we have categorized some ligands that they are going to donate, right? Okay. It's not just they should have lone pairs, there are other factors also. There is alignment, there is its electronegativity. There are so many factors that will rule when we talk about the donation of lone pairs, right? Okay. Yes, we'll do that, Sai Priya, will do that, right? Okay. Yes, now focus here. This is chromium NH3 thrice H2O thrice Cl3. Right, now how do you name this? Firstly, if you see, this is your cation and this is anion. Firstly, I'll write this is 1 and this is 3, so this will become 3 and this will become 1. This is positive, this is negative, so that will be my coordination and that will be my charges. So let's calculate the oxidation number here. Chromium is X, right? Plus ammonia is 0 plus water is 0 is equals to plus 3. So chromium will have plus 3 oxidation state. That's why it is written in Roman numerals, right? If you talk about this coordination sphere, first you will write ligands. You have amine here and you have aqua, right? So A is cancelled. Now this is M and this is Q. M is before Q in alphabetical order. So you'll write triamine, triaqua, triamine, triaqua. Then there is name chromium. Why we have not written chromate? Because the complex entity is a cation. If it is cation or neutral, we will name it simply the same name. There is no 8 now. So chromium, 3 is the oxidation state. And for counter ion, we don't write trichloride. No, we'll simply write chloride. Because if you say, ma'am, we are not representing this is 3. Because of this 3, it is 3 positive. And because of this 3 positive, the coordinate oxidation number here is 3. So without mentioning tri, you have mentioned tri. Okay. What about this one? What about this one? Yes, everybody. Thank you, Sai. Acha, now let's see this one. In this case, have you noticed one thing? This is also coordination entity, this is also coordination entity. This is positive, this is negative. So we can do hit and trial here. If I take this as 1, this as 1, this will be 1, this will be 1, this will be negative, this will be positive. Now if I see the oxidation states here, this is X plus 0 is equals to plus 1. So X is equals to plus 1 and silver exists in plus 1. Here this will be x minus 2 is equals to minus 1, that is x is equals to plus 1. So here also the oxidation state of silver is plus 1. Firstly, we will write the cation. In the cation coordination entity, firstly we will mention the ligands, then we will mention the central metal atom, right? So firstly, when we mention the ligands, it is going to be diamine, then the coordination entity is altogether positive, right? That means silver is going to behave as silver only. So we'll say silver oxidation state is 1. Then what about this one? Here you have dicyano, you will write 2 cyanide, so you will write dicyano or cyanido, right? Then now silver is not written. Now instead of silver we have written argentate here. Who will tell me the reason behind that? Why we have written argentate here? Why not silver? Ma'am, because argentate is written because this coordination entity is negative. That is why the central metal atom will change its name. Right? Okay? Done. Next is this one. Here you have 2, 3. So 2, 3 means here you will have 2, here you will have 3 and here you will have 2. This will be positive, this is negative. If you see the oxidation number here, this is X for cobalt plus this is ethylene diamine, that is 0 only, right, is equals to plus 2, plus 3. So this is going to have plus 3 oxidation state, right? Now firstly we will write the ligands. Ligand is only ethylene diamine, but ethylene diamine itself has di, so it will be not written as triethylene diamine, it will be written as tris, then it will be bracket ethylene diamine or ethane 1,2-diamine, both are the same things, right? Then you will write cobalt. Why it is not cobaltate? Because coordination entity is positive here, right? Cobalt oxidation number is 3 and this is the counter ion, that is sulfate. Tell me. Clear everyone? Clear? Any problem in understanding the IUPAC naming? I have given you examples as well here. Tell me if there is any problem here. Tell me. Any problem over here, right? Now let's talk about the set which does not have ambidentate. Okay, you have to tell me which of the following set does not have ambidentate ligands. Ambidentate ligands, see, this is not, oxalato is not ambidentate. Which does not have, there should be at least one ambidentate ligand. So this is ambidentate, this is ambidentate. Here none of them are ambidentate. This is bidentate, this is bidentate, this is monodentate. Here this is ambidentate, here this is ambidentate. So this is the only option where none of the ligand is ambidentate that has been asked in JEE 2023. A very, very simple question, right? Yes, Pritija. But please let me focus. In 3 hours, if I have to complete a big chapter, otherwise tell me, are you ready to be here till 5 a.m.? No, right? You also want to save your time, right? Pritija, then tell me one thing, that do you want me to read out your quotes in the class? I don't want to disrespect you, but you should have that much common sense, right? Without a break, I am speaking, right? Without, why? Just to save your time, just to save those students time who actually want to study something, right? So I can't waste anyone's time on quotations. Please understand that. Don't create this kind of thing in the lecture, right? This is not going to make me happy. This is going to irritate me only, right? So answer is B is the correct answer. Tell me. Clear everyone? Next question, if you see, the IUPAC name of this particular compound they are asking. Let's see how many of you answer this question. Let's see how many of you answer this. If you see this here, right, this is K3. I'll just write it here, K3CO. What is the ligand? Tell me, what is the name of the ligand here? What is the name of the ligand? See, this is 3, this is 1, so it will be 1 here and 3 here. So it will become K positive and it will become COC2O4 thrice 3 negative. Okay, so if you write the oxidation state, this will be X plus minus 2 into 3 because the ligand is oxalate. And this is minus 3. So x minus x is equals to minus 3, x is equals to plus 3. So oxidation state should be plus 3, which is in all of them. Now, if you see this here, this is a negative coordination entity. So cobalt is not possible. You need to have cobaltate. So these two options are eliminated. Then guys, we know that in this case, you need to have simply trioxalato, right? So you will write C as the correct answer here. So simple, you have trioxalato, potassium trioxalato, cobaltate 3 will be the correct answer. C is the correct answer. Tell me guys if that is clear to all of you or not. Right everyone? Is that clear to all of you or not? Yes. Acha, one more thing I'll just write here before going to Werner's theory. One of you were asking me about chelate complexes. See, chelate complexes are simple. For example, you have a metal and it is existing in octahedral geometry, and let's say it is having some monodentate ligand, let's say chlorine or NH3, right? Are they forming any ring? They are not forming any ring, right? For example, you have a metal which is again existing in octahedral complex, but now it is forming a ring. It is a bidentate ligand. Let's say it is ethylene diamine is connected, ethylene diamine is connected here, ethylene diamine is connected. How come it is forming a ring? Because ethylene diamine will be something like this. C and C, this is N, this is N, and both the nitrogens will be donating, right? So 1, 2, 3, 4, 5 membered ring it will form. So because of this ring, they get extra stability. That is called as chelate effect. More the number of rings, and that will give maximum stability to that coordination complex. Okay, right? Now 3 hours we are studying some chapters for the first time. Yes, Harshit, I have taken this particular lecture in such a way that in 3 hours everything I can cover. Okay, right? Yes. Done? Okay, now let's understand. Werner's theory. If you talk about Werner's theory, everyone, let's talk about Werner's theory. Yes, students. What is Werner's theory? This is the first theory that we have. See, Werner theory tells you about primary valency and it tells you about secondary valency, right, for a metal. Now, in Werner theories, it was based on one experiment, and this experiment firstly we'll talk about. Werner theory, firstly, he has taken compounds here like COCl3.6NH3, COCl3.5NH3.4NH3.3NH3, and what he saw that in this case 3 moles of AgCl are precipitated out. Now remember that whenever you add AgNO3 to Cl negative, it will give AgCl. So more the number of Cl negative you will have, more will be AgCl, right? So if I am saying 3 mole of AgCl is produced, that means in this compound outside the coordination bracket you have 3Cl. That means this will have CO. This will have CO. How many? 6 ammonia are there. NH3 6 and Cl3. That means this is the coordination compound that you have. Here 2 mole means 2 Cl are outside. So it will be cobalt, NH3 is 5 and 1 Cl is there, right? Because total 3 Cl you have. 2 are outside, so 1 will be inside, right? Then guys, next is you have 1 Cl outside. So this is 1 Cl outside, right? 1 mole of AgCl means 1 Cl outside. So this is cobalt. Cobalt. How many ammonia you have? 4 ammonia, right? So 4 ammonia. And if out of these 3 Cl, 1 Cl is outside, you are left with 2 Cl. So 2 Cl will be inside. That means this is the coordination compound. Then if I see no Cl negative, no AgCl PPT is formed, there is no Cl outside, so it will be cobalt, ammonia is 3 and chlorine is also 3. So this is the compound that you will have, right? Can you see one thing here, everyone? Can you see one thing here? You can see over here that what is happening, that by just knowing that how many AgCl precipitates are formed, I am able to make two things. I am able to understand that what is the coordination complex, right? What is the formula of coordination complex? So he made a theory that every single complex is having different formulas. So he made a theory on that. He said that if you talk about complex of this, that is yellow in color, this thing is also important. This compound is yellow in color, this is purple, this is green, and this is very important. One very important thing I'll talk about. This is 1 Cl, this is no Cl outside, that is violet in color, right? Now what you will see, every single compound has different AgCl precipitates, it has different formulas, and it also has different colors. That means something different is there, right? So he said that in reality, that what is there, he said that basically we have two kind of valencies. He postulated this theory based on that experiment, that basically we have two kind of valencies. First is primary valency, other is secondary valency. He said that primary valency is very simple. Primary valency is nothing but it is the oxidation number, and secondary valency is nothing but it is the coordination number. So he said that if you talk about this particular compound, there are 6 ligands here, right? So primary valency, secondary valency is going to be 6, that is the coordination number. You can remember this by CS. C means coordination number, S means secondary valency, right? Secondary valency is 6, primary valency is 3, because 3 chlorines are responsible for your oxidation number. Now let's talk about more about this thing here. Let's talk more about this thing here. If I say that, okay, now I'll just show you that one question that I skipped here. Because based on this thing also, a lot of questions are asked. Wait a minute. Yes, this was the question. The secondary valency and the number of hydrogen bond, this is 2021 question. Hydrogen bonded water molecules in this particular compound is how many? Firstly, they are asking you the secondary valency and the number of hydrogen bonded water molecules, right? So what is the secondary valency? Secondary valency is the coordination number. What is the donating sites here, right? How many donating sites are here? And number of hydrogen bonded water molecule that has hydrogen bond with each other. So let's talk about this thing here, right? Okay. So if you talk about CuSO4.5H2O, this is going to make this kind of coordination complex. So if you don't have knowledge about the coordination complex, then it is going to be a difficult question for you. CuH2O4, 4 water it is using, right? And one SO2 molecule is outside and one water molecule is outside. Okay? That means the counter ion is this one. This is the counter ion. You can say this is the counter ion. And this is the coordination. This is the ligand. So if you see this here, Cu is coordinated with 4 water molecule and 2 more oxygen atoms from sulfur ion, and 5th water molecule is hydrogen bonded with it. So what is the secondary valency? What is the coordination number? It is 4, because 4 H2 are there, and if you talk about number of hydrogen bonds per molecule, in one molecule you have one hydrogen bond, where this water is hydrogen bonded with this complex, right? So here you have one hydrogen bond, so total it is going to be 4 and 1. So answer is B is the correct answer. This was an interesting and important question. Okay, yes, thank you Gautam, thank you so much, thanks a lot. Yes, tell me. Done, everyone? Next. Beta, don't worry. In detail, we'll do the lectures. In detail, thermodynamics, redox and all, we'll do that. If you're asking me about class 11th, if you're JEE 2027 aspirants. Right? Okay? Yes. Acha, this we have done already. Then we have next thing, that is, let's see some questions on Werner theory. JEE 2021 question. Yes, everyone, JEE 2021 question. Let's talk about that. Right? Yes, Ritij, yes. So here 3 moles of EgCl get precipitated when 1 mole of octahedral coordination come out. 3 moles of EgCl are precipitated. That means 3 is outside. Okay, so empirical formula is this thing, right? And reacts with excess of silver, 1 mole of octahedral coordination. Octahedral means 6 ligands. Ammonia are 3, water is 3. So compound, I know what is the compound they are asking me. This compound reacts with excess of silver nitrate. 3 moles of this is precipitated when 1 mole of this. Okay. Number of chloride ions satisfying the secondary valency of the metal ion. But firstly tell me, secondary valency means coordination number. Is there any chloride ion that is satisfying the coordination number? Tell me. Is there any coordination, any chloride ion that is satisfying the coordination number? Can you see anything here? No, right? So answer is 0 is the correct answer, right? And sometimes what happens, so I'll just give you one example here. For example, sometimes what happens, let's see, I'm just taking a random example. Let's say you have CONH3, 5, this is Cl and this is Cl2. Okay, you have this compound. This compound has no relation with this particular question, right? It has no relation. I'm just giving you what do you mean by satisfying, right? So what if they give you primary valency satisfied by which of the following? So if you see this here, right, this is secondary valency is satisfied by 2 chlorine ions. sorry, secondary valency is, secondary means the coordination number is satisfied by 5 NH3 and 1 Cl. This chlorine is responsible for coordination number 6. That is absolutely correct. But the problem is that students write this thing wrong, right? This thing students do a lot of mistakes. This is primary valency. Now tell me, primary valency is satisfied. Primary is oxidation number. Oxidation number. How do you calculate oxidation number? Tell me. How do you calculate oxidation number? You calculate it like x plus 0 minus 1 equals to minus 2. So are you not writing that this is minus 1? Are you not writing that this is minus 2? Arey, wait a minute. This is not minus 2 here. Wait a minute. If this is 2, this will be 2. This is 1, this will be 1, this will be plus, and this will be minus. So it will be plus 2. Okay? Overall, it will be plus 2 here. So I'm going to write plus 2 here. So can't you see that we are adding the charge on this as well as the charge on this? So there are 3 chloride ions. This is a very important question that students usually do mistaken. Primary valency is satisfied by not 2 but 3 chloride ions. Because oxidation number is not only about counter ion. Oxidation number is about all the charge species that you have, right? What is the charge over here? What is any charge over inside any ligand which has charge? So this primary valency is satisfied by 3Cl negative. Tell me if that is clear, right? Okay. Okay, Gautam will definitely do biomolecules revision as well. You can just write down in the comment section after the class what are the chapters that you want me to take up, right? What is your pinpoint for JEE 2026 aspirants I'm talking about? What are the chapters that you want me to take up? I'll take those chapters. You just have to write down the list of those chapters, okay? Right? Tell me. Yes, Dharnish, chelating ligands, because beta always ring is more stable, right? Ring is more stable as compared to open chain, and that's why they are forming a ring. Ring is making it more stable, a more stable structure. That is how chelating ligands are making it stable. Okay? See. Then next we are going to talk about is VBT, valence bond theory. Ready everyone? Valence bond theory. Right? Okay, general. Beta, general OC, how many times do I do that? I have just done that, GOC. I have done it. Okay? Isomerism, you can watch the full detailed lecture on that. Right? Okay? Chalo. Now let's talk about VBT. Just give me a second. I just realized that I don't have the structures that I wanted to show you. Just give me a second. Yes. Okay. Yes, students. Chal. Yes. Now, let's talk about VBT theory. Let's talk about VBT theory, everyone. Ready for it? Beta, isomerism and coordination I'll do today only. If you're asking me about it, I'll do it today only, right? So, see, we have some important structures in VBT. In VBT, we'll talk about hybridization, we'll talk about the structures. So, first kind of structure is tetrahedral structure. That looks like this. This is tetrahedral structure. Then there is octahedral structure that looks like this. 180 degree, these are 90 degree, 90 degree, 90 degree. So it's like a square, right? You have a square. This is square planar. And here you have two more ligands at 90 degree. That is octahedral, right? Okay. So now let's discuss about how you will tell that this is tetrahedral, this is square planar, this is octahedral. How do you define that from VBT theory, right? So simple thing is that in VBT theory, first thing is how it was postulated and how we study it is entirely different. How it was postulated is, firstly they gave us that the scientists, when they were doing experiment, they, from the experiment they find out that this is diamagnetic, this is paramagnetic. Once they know this is diamagnetic, this is paramagnetic, once they are sure about this thing, that okay, this thing is diamagnetic, then what they studied, they said why it is diamagnetic. Then they went through study the hybridization and structure, right? They had no idea which ligand will cause pairing, which ligand will not cause pairing. This is the real VBT theory, right? But how do we study it is, we take the application from CFT theory, that is strong field and weak field ligand. Before studying VBT, we study which will cause pairing, which will not cause pairing. Then we study hybridization, then we study structure, and we tell that this is di and this is paramagnetic. Okay? Because for our question, that sequence is important for us, right? So let's do that. So here it is. According to this theory, metal atom and under influence of ligands can use its N-1D, NS, NP, NS, NP, all these orbitals for hybridization. They can give different shapes and geometries. So postulates are, the central metal atom has empty orbitals for accommodating electrons. Central metal atom, it has vacant d orbitals where it can accommodate the electrons donated by ligands. Second is, the formation of complex involves a reaction between Lewis base, which is electron donor ligand, and Lewis acid, which is metal ion. They react with the formation of a coordinate covalent. Now, VBT theory is directly saying that it's a coordinate covalent, that is dative bond, right? Then, hybridized orbitals are allowed to overlap, right? Hybridized like sp3d, sp3d, sp2, these are hybridized orbitals. They overlap with the ligand orbitals that can donate electron pair for bonding. That means central metal atom, they have empty d orbitals which are hybridized. For example, they have 1s and 3p orbital, they hybridize to give sp3. Now these 4 sp3 orbitals will accommodate the ligands, the electrons that are given by ligands, right? So next is, under the influence of strong field, electrons can be forced to pair up against Hund's rule of maximum multiplicity. Strong field, they will again do pairing. So first is strong and then there is weak field ligand. Strong field ligands like NH3, EN, Ca negative, CO, they are very strong field ligands. See, there are exceptions also in this VBT. That's why this is not going to be a very successful theory. Okay, you will study a lot of exceptions here. This is what we are going to see here, Dharnish. In 10 minutes, you will be able to understand how do we take the hybridization. Okay. See, firstly, these are prerequisite of knowing VBT theory. If you don't know this, then that will be tough, right? So strong pairing is by NH3ENCNCO. They cause pairing. These are the compounds these are the ligands which do not cause any pairing, right? So before going towards the exception, let me teach you some important points here, right? I'll just tell you how do I do that. First thing is, if the coordination number is 6, then definitely it is going to be octahedral. Either the hybridization will be, for coordination number 6, hybridization can be 2, either sp3d2 or it will be d2sp3. Only two possibilities are there, either sp3d2 or d2sp3. When d is outer, that is called as outer octahedral complex. When it is d is inner, then it is called as inner octahedral complex, right? Then guys, if you talk about coordination number 4, in coordination number 4, two things are possible. If it is sp3 hybridization, that will be tetrahedral, that is this kind of geometry will be there, right? But if I say it is dsp2, if I say it is dsp2, then it is going to be square planar like this, okay? So that means our main motto is not calculating the structure, understanding the structure. Our main motto is understanding the hybridization. You should be able to tell that what is the hybridization of this thing, right? So to understand the hybridization, firstly I'll take some examples here, right? First example is this one. So in this example, I'll do one thing, okay? What is that thing that I'll do? Let's say it is not given that, okay, so what I'll do now, wait a minute, right? Wait a minute. I'll tell you how in simple steps you will do this, right? Okay. I'll give you some steps which you are going to follow, right? And you will get your answer always correct. Okay. Suppose this compound is given to you. I'm assuming that they have not even given that this is para or diamagnetic. Let's assume that they have not given that this is paramagnetic. See, in reality, it is experimentally firstly find out whether it's para or diamagnetic, but we are thinking that in this question, we don't know whether it's para or it's diamagnetic, right? So firstly, what you will do? Firstly, always you will see the oxidation. The first step is to calculate the oxidation number. So first you will see the oxidation number. This is going to be X for cobalt, minus 6 for fluorine. 6 fluorine means 6. And it is going to be minus 3. So X is going to be plus 3. So cobalt has oxidation, has atomic number 27. That means it is 4s2 3d7. This should be on your tips, how to write the electronic configuration of 3D elements. For VBT theory, for understanding VBT, CFT theory, you should know how to write electronic configurations. Once you have calculated oxidation number, you will write the electronic configuration. Then you will take out 3 electrons from here. Always remember, electrons are first taken out from 4s, then 3d. So it will be 3d6, right? So 3d6. All of you know, right? How to? All of you know the 3d orbital electronic configuration, right? Yes, you are confident on that. Is it? Yes, everybody. Do let me know in the chat box, right? So if you see, this is 3d6. Now I am saying this is a weak field ligand. It will not cause any pairing. No pairing will be there. So it will be 1, 2, 3, 4, 5 and this is 6. Now can I see that there is, I need vacant orbitals. So can I see any vacant orbitals? No. So what is the what is exactly the apna coordination number here? Coordination number here is 6. So I need to have 6 vacant orbitals. So it will be 1, 2, 3, 4, 5, 6. That is nothing but it is D. It will be sp3 d2. That is outer octahedral, right? Outer octahedral, right? So first thing is they ask you the hybridization, then they ask you the geometry, then they also ask you if it is para or diamagnetic. Because it has unpaired electron, it will be paramagnetic. Number of unpaired electrons are 4. And always remember that diamagnetic, where all the electrons are paired, when even one electron is unpaired, that is paramagnetic. And if n is the number of unpaired electron, that mu is equals to, that is magnetic moment is equals to under root n plus 2. But if you have it as 1, 2, this is a direct trick. Okay, for 1 it is 1.7, for 2 it is 2.8, 3 it is 3.9. Wait a minute, no, like that, yes, 2.7, this is 3.8, like this, it will be 8. 3.8, 4.9, 5.9. So it is 0.7, 0.8, 0.8, 0.9, 0.9. That is the direct way of calculating the magnetic moment here. So if you see this, you can just directly write mu is equals to 4.9 Bohr magneton. Right, now few more things that you can write here, that is few more things here. How many if you see that the complex is having unpaired electrons, that means it's a high spin complex, or you can say spin free complex. Okay, high spin complex, spin free complex, paramagnetic, and there's so many things they can ask you from just one thing, right? Okay, so all these points I have already written, it is high spin, this and that. So I would just delete this particular page. Next is NH3. So in the similar way, we are going to solve this as well. How many of you are going to do this along with me? How many of you will do this along with me? Tell me. How many of you will do this along with me? Firstly, tell me that how do you calculate the oxidation number, everything here. Right, everyone? Ready for this? Students, tell me. What is the first step? Tell me, what is the first step that I taught you? What is the first step? The first step here is calculation of Yes. Tell me, guys, what is the first step here? What is the first step? What I told you, what you have to do first when you see these kind of questions? I can see everything except for the question that I have asked. I can see every single thing. Ma'am, will weak field ligand has diamagnetic nature? Any exception? There are a lot of exceptions. That's why I have made specially one single page is entirely on exceptions. Okay, so exceptions I'll tell you. Firstly, we'll do all these examples to understand what is the reality. Then we'll talk about exceptions as well. Okay. First is calculation of, very good, only theory is giving me the answer. Yes. So calculation of oxidation state. So this is x plus 0 is equals to plus 3. So cobalt is actually 4s2 3d7. And when you take out 3 electrons from here, this will become 3d6. So here, but ammonia is a strong field ligand. It will cause pairing. And that is the reason it is 1, 2, 3, 4, 5, 6. Now if you see what is the, for 6 coordination number, either you can have sp3d2 or d2sp3. So it will be d2sp3. 1, 2, 3, 4, 5, 6. Yes, 6 vacant orbitals you have here. So answer will be D2sp3. That is also called as inner octahedral complex. That is also called as low spin because unpaired electrons are very less, or it is also called as spin paired complex. It is not spin free, it is spin paired complex. So these are the different names that it has. If you talk about the electrons, if you see this here, this is dimagnetic in nature, so you can say it is diamagnetic. Why it is diamagnetic? Because there is no unpaired electron here. Here number of unpaired electron is 0, so mu is also going to be 0 here. Tell me, clear everyone? This is how you're going to solve these kind of questions, okay? We'll have a talk about it in some other video, guys. Today, see, I don't have that much time to talk about such sensitive issues, okay? So, that is also done. Yes, wait a minute. Yes, okay. Then let's talk about when you have coordination number 4, what are the possible things that we see, okay? So, first thing is, tell me everyone, firstly what we do. Firstly, we calculate the oxidation number. What is the atomic number of nickel? What is the atomic number of nickel? Everyone, what is the atomic number of nickel? Can I see that in the comment section? Yes, Rithwan, we will see spectrochemical series now. There you will see I have made a trick as well on spectrochemical series. There you will get to know about strong field, weak field, ligand in detail. Okay? 28, right? So nickel is 28. So if I see this is oxidation number, it is going to be X minus 4 is equals to minus 2. So it is going to be plus 2. So nickel, we know that this exists in 28, that is 4s2 3d8. You take out 2 electrons, it will become 3d8. Now, when it is 3d8, now tell me, is this a strong field ligand? Chlorine is a strong field ligand or a weak field ligand? Chlorine is a strong, halogens are strong field or weak field? Who will tell me about it? Will it cause any pairing or will it not cause any pairing? Is halogen a strong field ligand or it is a weak field ligand? Will there be any pairing or there will be no pairing? Every day I come here and students are telling me, ma'am, you look like this, you look like that. Yeah, I look like Diksha Kaushal only. I want to look like myself only, right? So I don't want to look like someone here. I have my own identity, right? Okay, but thank you, right? So weak field, right? So it will be no pairing. So it is 1, 2, 3, 4, 5. First your degenerate orbitals are filled. Then 6, 7, 8. And we are looking for unpaired electrons. So, and we are looking for 4 empty d orbitals and we have this, right? So I can say this is sp3. So hybridization is sp3. If hybridization, if I am saying, if the hybridization is sp3, this is going to be tetrahedral in nature, right? This is going to be tetrahedral in nature. Is there any unpaired electron? Yes. So that is why it is high spin. Or it is also spin free complex. Spin free complex. Spin free complex, right? Okay. Yes. Now tell me whether it's paramagnetic or diamagnetic. Very good. It's paramagnetic. It is also written there. Paramagnetic because of unpaired electrons. How many unpaired electron? It is 2. So what will be the Bohr magneton? For 2 it is 2.8. That is approximately in integer you will say 3. Right? So 2.8 Bohr magneton, that is the correct answer. And these are the things that they can ask you from here. Right? Okay. Now, next is, let's talk about the next thing, that is, okay, this we have discussed. This we have discussed. Now let's discuss this one. Yes, everyone. Tell me. Sure, let's solve this. Let's solve this in an easy way, right? Till now, I am not taking any exceptions. Okay, I am just taking simple compounds that they ask you. Then I'll also tell you about the exceptions that we have, right? Okay, tell me. Firstly, what is the oxidation number here? What is the oxidation number? And for nickel, what is the oxidation number here? Cn is a negative ligand or a neutral ligand? See, how many things you need to know about ligands. You should know the charges on ligands, everything you should know, right? Okay? Yes? Very good. Yes, Batman, we will definitely give you PDF also for this session, so don't worry about that. Yes. So here if you see it is 2, so x minus 4 is equals to minus 2 is equals to plus 2. So here nickel is in 28, so it is 4s2 3d8. Nickel 2 positive will be what? That will be 3d8. Now tell me, is this a strong field ligand or it's a weak field ligand? What kind of ligand Cn negative is? Very good. Very good, Bonthu. Very good. So it's a very good, Subhash. So it's a strong field ligand. So it will cause pairing. So it will be like 1, 2, 3, 4, 5, 6, 7 and 8. Now if you see, you need 4 vacant orbitals. So it will be d sp2. After that, you have only these orbitals. So answer is going to be dsp2. For dsp2, the geometry is square planar, right? Once the geometry, we are saying that the geometry is square planar. Yes. Very good. Is there any spin, unpaired electrons you can see? No, ma'am. That's why it is low spin complex. Before this, I wrote high spin only, no? Yes, yes. Okay. Low spin complex, it is also called as spin paired complex. Spin paired complex. It is also using inner d electrons. That also you should remember. Then this is diamagnetic in nature. So number of unpaired electrons will be 0 here. So magnetic moment is going to be 0 here. Okay? Tell me. Any problem? Yes. Now, those who were confused in VBT theory, tell me if now also you have any problem, because now we are going to discuss about the exceptions of VBT theory, right? The exceptions of VBT theory. Let's discuss about that. The exceptions of VBT theory, let's discuss about that. Yes, everyone. Ready, everyone? Ready for the exceptions? And how very few likes you guys have given. What conjuicy this is. Huh? Very few likes. Why? Are you not able to understand things or what? You want everything for totally free of cost, right? You don't even appreciate a bit. That's so sad, right? So, mm, few more model PYQs. Grow and grow. Definitely, beta, we will do more only dedicated PYQ sessions as well. We will do. Don't worry, right? Okay. Yes. If few members are there, then those members at least should like, and they should at least comment, right? If 23 to 27 students are here, and I want these much comments in the comment section, I want that, right? So yes, every single student who is religiously watching these lectures, right, write down in the comment section, right? That gives us motivation, right? Okay. Oh, thank you so much, Pritija. Thank you so much. Yes. Huh. Let's see these exceptions. Cobalt 3 positive is bonded with water and oxalate, which are weak field ligands. But if you have cobalt 3 positive, they will behave as strong field ligands. Copper 2 positive with water. Water is actually a weak field ligand, but here it will act as a strong field ligand, right? Then you have nickel 4 positive is bonded with fluoride ion. It is bonded with F negative. Then ligand act as strong field ligand. So if you have fluoride F negative, then this Ni4 positive is going to behave as a strong field ligand. Okay. This nickel 4 positive is going to behave as a strong field ligand if there is fluoride ion. Fluoride ion is a weak field ligand, but here with Ni4 positive, it will behave as a strong field ligand. Then you have cobalt 3 positive and iron 3 positive. Ammonia acts as a strong field ligand, right? Then you have Fe3, Fe2 positive MN3 bonded with ammonia. They act as a weak field ligand, right? Then you have compounds of PT-PDAU. That means compound of 4D and 5D series. Prefers, this hybridization means they prefer pairing with all. That means 4D and 5D series elements, whether you have strong field ligand or you have weak field ligand, they will cause pairing, right? Okay, so these are some important exceptions, and that is the reason this theory was not so useful, right? Why? Because there are so many abnormal, the answers were not correct in some of the cases. So we regard it as exception. But when there are too many exceptions, that means the theory is a failure. Okay. So limitation is that it does not give quantitative interpretation of thermodynamic or kinetic stabilities. It does not make exact prediction regarding tetrahedral square planar structures. It does not distinguish between strong field and weak field ligands. Right? Okay. Now, next is, let's understand amongst, now question is JEE 2022 question that says they have given you 3 compounds here. Spin lonely magnetic moment, inner orbital complex that absorbs light at shortest wavelength is this. Okay, so the one that absorbs light at shortest wavelength. If you see these 3 compounds, simple thing is energy is inversely proportional to wavelength. Strong field ligand will have a lot of energy, hence their wavelength will be very small. And out of these, I can see strong field ligand, this is the strongest field ligand. So this will give you the shortest wavelength, right? And you should be able to calculate the magnetic moment of this one. So we are going to calculate the magnetic moment of this one, right? That is having the shortest wavelength. Okay, so Cn negative is a strong field ligand, and then NH3, hence this is having the highest energy because it's a strong field ligand, and that's why it has shortest wavelength, right? So now let's understand this. If you see K3 FeCN6, oxidation number will be X minus 6 is equals to, this will be 3, this is 3 negative, X is equals to plus 3. So if you see, if iron is nothing but 4s2 3d6, iron 3 positive is nothing but 3d5, this causes pairing, so it will be 1 2 3 4 5 s, then this is p3. If you fill the electrons 1 2 3 4 5, and here this will be d2sp3. So it's an inner orbital complex, and it is 5 unpaired electron, here it is 1 unpaired electron. So magnetic moment will be 1.7, that is equals to 2 Bohr magneton. So nearest integer is going to be 2 Bohr magneton is the correct answer. So answer is 2 is the correct answer. Tell me, is that clear, everyone? Any problem you have here? Any problem you have here? Right? Let's see the next question that was asked in JEE 2021. JEE 2021 question, everyone. Yes. Tell me. So, JEE 2021 question, according to the valence bond theory, hybridization of sentimental atom is this for which of the following compounds? Okay, hybridization has to be dsp2. That means there should be pairing. So definitely this will not cause pairing, so this is already ruled out. This can be the correct answer. This is also Cl, so it is also ruled out. This can be the answer, right? This is Ni. See, I'll see the strong field ligand here. Maximum strong field ligand is this one, so I'll choose this one, right? Because here both are strong field, but here I'll see the chances are more. So this will be 2 negative. So here X is equals to plus 2. Nickel is existing. Nickel plus 2 is nothing but 3d8. And there is pairing here. So what I'll do, wait a minute. 1, 2, 3, 4, 5. And this is S and this is P3, right? When you fill the electrons d8 in a strong field, 1, 2, 3, 4, 5, 6, 7, 8, and this gives you dsp2. This gives you dsp2. And that is the correct answer. So answer is D is the correct answer. Okay? Right, everyone? Tell me. Is that clear? Is that clear? Okay? Yes. Tell me, everyone, if that is clear to all of you or not. Right? Yes, students. And in platinum compound, always there will be pairing. Okay, there is, whether it's a strong field ligand or a weak field ligand, it will cause pairing. Okay? Yes? Yes, everyone, do let me know. See, so many comments I have. I think the comments you are not able to see. So let me just show you the comments here. So many beautiful comments that we have. So just enrolled in crash course, feeling super confident already. Thanks for bringing this crash course. I was stuck in some Eclair questions. It will help me. Everything from notes to PYQs to doubt discussions. Best decision ever. Everything notes to this. Everything is there. Thank you so much, sir. Feeling so confident. Price range, no one ever gives the proper test series, and here we're getting so much along with Telegram mentorship. Thank you so much. That's really, really, really awesome, students. Isn't it? Isn't it awesome? Right? So, so happy to see these kind of comments from students that, they give so much value to the things that we do for them. Right? So, this is what we all want from you is just study as much as possible. We are here to help you. Please study, focus, focus, focus. Right? This is what we need from you. Right? Okay. Shri, I will teach at this speed only. If you think the speed is slow, you can watch it on the recorded version. Right? Okay. Done? Chal. Now let's see crystal field theory. CFT. Array? What is this? Okay, what? OMG, I never knew that this kind of thing is there. So many hearts, guys, I am giving you. Are you also giving me these kind of hearts or not? Oh my god. I can fill this whole. This is for Children's Day, and it has just passed. So these many hearts I am giving you. And I'm also giving you some stars here. I'm also giving you some stars because you guys are my stars, right? And I also want to give you some smiley emojis, right? Because I want you to smile, not to become sad. Sad emojis are outside, outside. Just essay I am doing, little bit relaxation you also need. So many moons we have. Oh my god. So many suns we have. Oh, ho, ho, ho. This is drawing by Diksha ma'am. Okay. So, let's see. Let me see if I can erase this or not. Huh, I can. Thank God. Yes. Okay. So, let's start with CFT, right? Okay, ma'am, please start. Yes, I'm starting. Okay. Yes. So, CFT, it is, like VBT was based on covalent coordinate bond. CFT is based on electrostatic bond, ionic bond. We are saying ionic, electrostatic bond here. It is electrostatic model which considers the metal ligand bond to be ionic, arising purely. So basically we are saying that this is purely ionic. This is not a covalent bond, which is a wrong thing. Arising purely from electrostatic interactions between metal ion and the ligand. Ligands are treated as point charges. What we say that the ligands are treated as point charges, right? Okay, that we are saying that anions are donating because of negative charge, and dipole are the neutral molecules are donating because of the dipoles, right? Five d orbitals in the isolated gaseous metal atom have same energy, they are degenerate, right? But this degeneracy is maintained if the spherically symmetrical field is negative, charges around the metal. This degeneracy will be maintained, but suddenly something will happen because of the unsymmetrical field of ligand. The degeneracy is lost and causing splitting in d orbitals. All you have to remember that when ligands are approaching, firstly the degeneracy will remain, but as they approach more closer, the degeneracy is going to break. Right? The pattern of splitting depends upon the nature of crystal field. So there are two kind of patterns. First thing is we'll discuss to understand the patterns. We'll discuss about d orbital. There are 5 degenerate d orbitals, right? dxy, dyz, and dzx, right? They all are between the axes, right? dxy, dyz, dzx are between the axes. Then we talk about ligands which are along the axis. So dx square minus y square and dz square are along the axis, right? Okay. See, we'll discuss about two fields here. One is octahedral and one is tetrahedral. So when we discuss about these two fields, right? Thank you, Ritwan. So when we talk about these two fields, see, one simple thing is that when I talk about octahedral fields, can you see it's like this is x-axis, this is y-axis, this is z-axis. It's like these ligands are also along the axis, right? So you also want to get into that IIT, your friend also wants to get into that IIT, there will be competition. You will not be like helping the other person, you will be like, huh, this is my competitor, right? So this also is along the axis. If the ligand is also approaching along the axis, and if the orbitals, the lobes of those t orbitals are also along the axis, then what you will see in case of octahedral, repulsions will be seen in dx square minus y square, dz square and the ligands, and hence they will be higher in energy. They will have high energy and less stability. When your competitor is with you in the class, you will not be stable, right? But when you talk about tetrahedral complexes, yes, it's like steric hindrance. Very good, right? Very good. So when you have tetrahedral complexes, they are not along the axis. It's like they are between the axis. This is y-axis, this is x-axis, so this is between the axis. So that is the reason between the axis will have more energy. So in tetrahedral complexes, the energy of dx square, dxy, dyz and dzx will be high. Okay, that is the first thing that we have. Right, glad to see you. Awesome, Manoj. Great. Next is, if you see, see, axial, this I have told you that dx square minus y square will feel more repulsion in case of octahedral. That's why they are raised in energy. Non-axial will be lowered in energy in case of octahedral complexes. In case of octahedral complexes, these two orbitals will be raised and these three orbitals will be lowered in energy, and that is why this is the diagram that you draw. 5 orbitals are degenerate, but after that they will split, right? And what you will see here, that this is barycenter. From the barycenter, the difference that they have is plus 3 by 5, and here they have minus 2 by 5 delta naught, right? That is the difference from the barycenter, right? Okay, these orbitals are called as EG and these are called as T2G. What do you mean by G? Any one of you? What do you mean by G? This is called as EG, this is called as T2G. G defines for gyrate. In octahedral complexes, you have gyrate. That is symmetry. That is why they are called as gyrate. EG, T2G. Yes? Shri, tell me exactly what thing you are not able to understand. Right? Okay? Okay, Shri. Bye. Right? So now, let's see. Tell me, is that clear to everyone? Right? Tell me about it if there is any problem in understanding CFT for octahedral complexes. In case of, see, splitting will be there in octahedral, splitting will be of dx square minus y square and dz square. Okay? This is a name that they give. Like your name is, like my name is Diksha, someone's name is Mahesh, Sahitini, Shreja, Shri. So you also have your names. Scientists have given name to them. EG. E means these two pairs. T2 means these three pairs. G means gyrate. So we have put here G. Right? Okay. Tell me. Tell me. Okay, chalo. Now, let's see 3 orbitals of lower energy set, that is T2G, right? That is nothing but dxy, dyz, and dzx. And higher orbital set will be dx square minus y square and dz square. Okay? That is your EG set. That is your EG set. Now, energy separation is donated by delta O. It is also called as crystal field splitting energy. Crystal field splitting energy, that is CFSC. Energy of 2 EG orbitals will increase by this, and 3 will increase, 3 EG will decrease by this. Okay, so now let's see. This delta O depends upon which of the following factors? The charge. First thing is, it depends upon the charge on the metal. What is the charge on the metal ion? Increases with increasing charge on the metal ion. For example, M3 positive will have more than M2 positive, then M positive. Okay? Then, because more is the positive charge, more will be the ionic interactions, more will be the splitting. Okay? Then, whether the metal is in the first, second, or third row of transition series. We know that 3D series, then you have 4D, and then you have 5D. So we know that in 4D and 5D, no matter whatsoever you have, they will always cause pairing, because the splitting will be so high that they have to cause the pairing. So down the group, its splitting, CFSC, will increase. That is the reason in 4D and 5D, you will only see low spin complexes. Okay, because in 4D and 5D, always the splitting, that means the splitting is always so high that, see, if the splitting is low, tell me one thing, a simple example I am asking you. If I say that there is no lift and you have to go to the 14th floor to eat pizza, you'll be like, I don't want to eat pizza, I'll stay at ground floor only. I go there, 14th floor, eat one slice of pizza and come back. I don't need that, right? If I say you just have to go to the second floor, you'll be like, okay. So now if the splitting is quite high, then you will not go above. You will get paired. If the splitting is less, if you have to go to second floor or third floor, then you can easily jump to the next floor, right? Same thing, ouch. OMG. I was just about to fall. Oh my God. Yes. So if I say here, the splitting is very high. That means splitting is so high that they will never go to the next floor. They will always cause pairing, and that's why they will be low spin complexes always, right? Then it depends upon the nature of ligand as well, whether it's a strong field ligand or a weak field ligand. If you talk about a weak field ligand, there are so many different things that we should know about weak field ligand. Let's write some more things about weak field ligand. Different ways of writing weak field ligand. Tell me, weak field ligand means the gap in CFSC is very less. Okay, so that means, what exactly is weak field ligand? That means CFSC is less. The gap is very less. If the gap is less, they can easily jump to the next floor. They will not cause any pairing. If there is no pairing, in that case, ma'am, there is no pairing. That means if they are not getting paired up, will they be low spin or high spin? Spins will be there, so they will be high spin complexes, which is also called as spin-free complexes. Spin-free, free spins are there, right? Okay. spin free complexes. And you know, they also have one more thing. If pairing is not causing, that means delta O. That means we are saying pairing energy is so high as compared to delta O that we are not able to cause pairing. Let's say you go to market to purchase something which is very costly and your pocket is not allowing you to purchase it. That means this pairing is so high as compared to that delta O. Okay? Right, everyone? Do let me know. Clear? Okay. What about this one? In this case, CFSC is, everything is opposite. CFSC is high here. Pairing will be caused here. If you know this concept, no, so many things will be quite easy for you. Spin. Acha, tell me one thing. This is a weak strong field complex. Yes, we have written it here. This is a low spin. This is spin paired complex. Spin paired complex. This is pairing energy is less than delta O. It is so less that, let's say you have 1000 rupees and you just have to purchase something which is 500 rupees. You can easily purchase that, right? So if pairing energy is less, you can easily cause pairing. Okay, right? So this one is quite important for you, that what kind of complex you have. This also we have seen that the order depends upon which of the following things. If you talk about 3D, 4D and 5D, 3D has minimum, then 4D, then 5D has maximum splitting. If you talk about tetrahedral, octahedral and square planar, square planar has maximum, then octahedral and then tetrahedral. Okay, right? And then we come towards the spectrochemical series, right? That is this one. Now, this spectrochemical series is defined based on the based on how much splitting something is causing, right? So you will see that halogens lies towards the weak field ligands, and CN, CO, EN, they lies towards the strong field ligand. Okay, right? Tell me. Right? Halogens lies towards the strong field ligand, and these lies towards the weak field ligands. Is that clear to everyone? Right? So one trick to remember this thing is, I broke Samantha's clock. She found out called Harsha. Nobody ever noticed. She found out called Harsha. Nobody ever noticed any cracked clock. Right? I broke Samantha's clock. She found out called Harsha. Nobody ever noticed any cracked clock. Okay, tell me. Done, everyone. Right, this is the spectrochemical series which is going to tell you how much splitting will be there. Then guys, if you see strong field ligand which will cause a lot of splitting, right, leads to absorption of light of more energy because the splitting will be very high, so energy will be very high, and lambda, which is inversely proportional to energy, lambda will be very less. Weak field ligand, where absorption of energy is very small because splitting is very less, so lambda will be very large. Okay. Then we have this formula where we write CFSA is equals to minus 0.4 number of electrons of T2G plus 0.6 number of electrons of EG, right? 0.4 and 0.6, you have to remember this, that's it. Actually, you know, if you see, ma'am, what is this 0.4 and 0.6? If you write 3 by 5 is nothing but it is 0.6. 2 by 5 is nothing but it is 0.4. So you can say plus 3 by 5 minus 2.5 or plus 0.6 and minus 0.4 as well, right? Okay. Now let's talk about tetrahedral complexes. In case of tetrahedral complexes, splitting is opposite, right? Here dxy, dyz, dzx are above and x square minus y square and dz square are below, right? So one thing you can surely write here, that this is T, T2 and this is E. E means dx square minus y square and dz square. T2 means dxy, yz and zx, right? And you will see that tetrahedral complexes are mostly, you will see that they are low spin complexes. I'll tell you how. Sorry, high spin complexes, I'll tell you how. See, in tetrahedral coordination entity, the d orbital splitting is smaller, right? D orbital splitting is smaller as compared to octahedral splitting. How much smaller this is? That delta T, if you see delta T is approximately half of delta O, right? So can you see this over here? Delta T is 4 by 9 of delta O. It is approximately half of delta O. That means this is very less as compared to delta O. That is why, if you see, that is why, because the splitting is very less, that is why you will see always, in most of the cases, you will see high spin complexes for tetrahedral. You will see for tetrahedral, high spin complexes are more common as compared to low spin complexes. Okay? Right, everyone? Okay, now the question is, why are tetrahedral complexes more stable? Why they are more stable? So first thing is that they are more stable because delta T is equals to 4 by 9, that is approximately half of delta O. Second reason is that for tetrahedral you have 4 ligands, so energy release will be according to 4 ligands. In octahedral complexes you have 6 ligands, so energy released will be according to 6 ligands. So energy released is more, that's why it is easy, it is more stabilized to form octahedral complexes, right? Then ligand is very large, and then the other point is ligand is very large, repulsions. Now what exactly happens? Why tetrahedral? If you say, in some cases we prefer tetrahedral, not octahedral. Why tetrahedral are preferred in some cases? First case is why tetrahedral. This case was why tetrahedral complexes are, no, this is not a point of more stable. This is a point why tetrahedral complexes are high spin, because of this reason, right? Okay. But now here we are discussing why they are more stable. Ligands is very large. So that is why if ligands are large, in the octahedral field, if the ligands are large, repulsions will be more. In tetrahedral field, the repulsions will be less, and that is the reason tetrahedral is preferred. Then D0, D2, D5, D7, D10, these complexes are more stable in tetrahedral field. These complexes are more stable in tetrahedral, right? That's why they are preferred. Okay. Then it also depends upon central metal atom. Central metal atom should be in the lower oxidation state. Then there should be weak ligand. Then only tetrahedral complexes will be preferred. Right? Okay. Any problem, everyone? Any problem? Tell me. Any problem? Any problem you have? Yes, everyone. Yes. Okay. Tell me, guys. That I can see. Let's see color in D block. Color in these complexes, why they show a very specific color. Color of substances is due to absorption of light of a specific wavelength in the visible part of the electromagnetic spectrum and transmission on reflection of the rest of the wavelength. So the color of the complex is complementary to that absorbed. So for example, I say this is the splitting of d orbitals. If you have an electron here, it will absorb some h mu and it will get excited to this place, right? So this is what we are saying. It is due to the absorption of light of a specific wavelength in the visible part of EM spectrum, and when it absorbs it, it will transmit or reflect it. The color that is complementary to that wavelength will be seen by our eyes, right? So this is the color wheel where we say that, for example, you have violet, then you will see yellowish red or yellowish blue. If you have green, then you will see orangish red or reddish yellow. If you have blue, you will see orange. So these are the complementary color to each other. This is called as Munchell's wheel, right? So these are the complementary colors that are seen when they are absorbed, right? So for example, you absorb bluish green, right? So bluish green will be somewhere here, right? So it is going to show something reddish, right? So it is showing you red color, right? Okay, so these are some of the examples. You can go through this, right? Then if you see relationship between strength of ligand and color of the complex, now what we say, if the splitting is larger, energy will be very high. That means lambda will be very less. So that you must know. We know longer wavelength means low energy, shorter wavelength means high energy. So based on longer wavelength, we have just seen a question, if you remember, where we studied about the magnetic moment. We discussed about this thing only, that there I firstly told you that Cn is strong field ligand, so it will cause highest splitting, so lowest and shortest wavelength, and that is why I selected Cn over there, right? Okay. Now, limitations of CFTs. This theory takes assumptions that ligands are point charges, but actually they are not. This theory follows anionic ligand should exert greater splitting, because ionic, if you talk about negative and neutral, uh, ionic interactions will be maximum in anions. But if you see spectrochemical series, in spectrochemical series, these anions are actually towards the, wait a minute, where I can see the spectrochemical series. Yes, these anions are towards the end of the series and neutral is towards the higher side. So that is the exception in itself, right? That will be the exception. Next is, it does not take into account the covalent character. It is completely saying then these are ionic compounds, but these are not ionic compounds. They have a coordinate covalent bond, and it is completely ignoring that particular part, right? Okay. There are other theories as well, but that is not in our syllabus. No, bacha, no darshan, it's not recorded, right? Okay. Yes. Yes. So let's talk about the next thing here, right? Arey bhai, Mohit, relax. Okay. Reaction of COH2O6 positive with excess of ammonia. Excess of ammonia, it is reacted in the presence of oxygen, results into diamagnetic compound. Number of electrons present in T2G orbitals of that product is. Okay. So let's talk about this particular question. Stop spamming, everybody. Please focus. right? So you have COH2 positive, it reacts with ammonia and O2. It is going to give you what kind of reaction? These 6 water molecules, aqua, will be replaced by ammonia, right? This is a very, very famous reaction. When it reacts with ammonia, it gives 1 electron as well. So if you see this over here, this is X plus 0 is equals to plus 3, cobalt exists in plus 3. Cobalt is nothing but 4s2 3d7, so plus 3 will be 3d6. So NH3 is a very strong field ligand in front of CO3 positive. Do you remember the exception? Do you remember the exception, guys? NH3 in front of cobalt 3 positive is a strong field ligand, okay? So it's a strong field ligand. That is the reason it is going to cause the pairing. So it will be 1, 2, 1, 2, 3 for octahedral complexes. So for 6, it will be 1, 2, 3. Because it is going to cause the pairing, so it is going to be 1, 2, 3, 4, 5, 6. And we know that this is Eg, this is T2G. So answer is going to be T2G6, Eg0. That is the correct answer. And hence 6 electrons will be there in T2G. Okay. Next question, that is based on again CFT only. So again they are saying if a molecule this is some molecule they have given. They are saying it absorbs a light of wavelength 600 nanometer for DD transitions. DD transitions it will cause. It absorbs a wavelength of this particular, yes. Good. So this particular wavelength for DD transition, then the value of octahedral crystal field splitting energy for this complex will be what? See, this is a very simple question. This is not even, this is E is equals to Hc by lambda. Put the value of H, put the value of C, put lambda will be equals to Hc by energy. Energy is not given here. This is what is given here. This is given in nanometer. So you'll put it in meter and you will put all the values and you will get your answer here, right? So this is all what you have to do. And what they're asking you, they're asking, array, very nice thing they have asked. Oh, even I missed it. This is tetrahedral. They are asking you octahedral. Awesome, awesome, awesome. This is tetrahedral. So here you will be able to calculate the delta tetrahedral. Then we know that delta tetrahedral is 4 by 9 of delta octahedral. So delta octahedral will be equals to 9 by 4 of delta tetrahedral. Simple. You will solve it and you will get your answer. Right? Delta octahedral is 9 by 4 of delta tetrahedral. You will put all the values and you will get your answer here. Right? So it's a very nice, interesting and different question, I would say. That was a different question, okay? So because, you know, the formula from structure of atom they have used along with coordination chemistry. Overall, the question is easy, but this is interesting. Okay? Yes. Next is, they are asking JEE Mains 2020 question for a D4 metal. Metal is D4. In an octahedral field, for the correct electronic configuration is what? Correct electronic configuration, ma'am. D4 metal ion in octahedral field. See, D4 metal ion, 1, 2 in octahedral field is this. D4 metal ion, guys. See, simple thing is, D4 metal ion in octahedral field. So they have not given us pairing energy is greater or this. So I have two ways of answering this. Okay? If I say delta O is greater than this, if I say delta O is greater than pairing energy, if pairing energy is greater. If pairing energy is greater, that means no pairing will be there. If pairing energy is less, that means pairing will be there. When pairing, no pairing is there, it will be 1, 2, 3 and 4. If pairing is there, it will be 1, 2, 3 and 4. Here it is going to be T2G3, EG1. Here it is going to be T2G4, EG0. Okay. So for delta O less than, we have T2G2, T2G3 EG1, T2G3 EG1. That is over here. This is correct, so this is not correct. If I say delta O is less than this, T2G4, this is also not correct. Delta O greater than P. Delta O greater than P. Then it should be T2G4EG. This is also not correct. So only answer correct is D. Okay? Understood everyone? Only the correct answer is only this one. Right? So see how, like, easy questions they are asking you based on this. Right? It's not like very tough questions they are asking you. They're asking you quite doable questions from coordination chemistry. Okay? Yes. Chemistry is a scoring subject. It is going to save your rank, always remember. It is going to save your rank. And it is the only subject that, little bit you study it in, little bit, then you will be able to, like, you will feel confident that I'll be able to do this, right? And there is a specific pattern. It's not like every question is different in chemistry. It's not like that. If you know the concept, little bit molded question they ask you, you will be able to do it, right? Okay. Yes. So now let's talk about metal carbonyls. Everyone ready for the next part, that is metal carbonyls? Yes. I know Mohit. What should I do? I know, what should I do? Right? Tell me. When you tell me, ma'am, you teach really good, I know that is because of my hard work, right? That is what I have earned. When you tell me, ma'am, you're so beautiful, this is not what I have earned, guys. That's genetics, right? So if you think that you're calling me beautiful and that will make me happy, okay, that's good. But happiness is when you tell me that, ma'am, yes, the content is good, ma'am. Ma'am, you are actually, ma'am, I'm able to understand everything, ma'am. Ma'am, I was able to solve the questions, ma'am. That makes me happy, right? So if you want to spam something, you spam that, right? Okay. Yes. Yes. So if you see this here, metal carbonyls. Let's talk about metal carbonyls, guys. Let's talk about metal carbonyls. Thank you, Ritwin. Yes, understanding everything you're teaching is really good. Thank you. Thank you, guys. Thank you. Okay, so ready for metal carbonyl. This is also one of the questions that they ask you in exams. See, it's a very simple topic. It's an easy topic, right? It's a very small topic also, right? And you will be surprised to see that, oh my God, that's such a simple topic, ma'am. I'm able to do that, ma'am. Yes. Okay, and I'll also tell you about effective atomic number. That's also a very small topic. Usually students get scared, ma'am, effective atomic number. Relax, you will be able to do it. It's quite simple only. Okay, so firstly, let's talk about metal carbonyls. So homolytic carbonyls, that means where the ligands are only carbonyls, compounds containing carbonyl ligands only, are formed by most of the transition metals, right? So if you see in these cases, what you have is a synergic back bonding, right? So what we know that ligand wants to donate, metal wants to accept, that is a general case, right? But sometimes it's like a general case is usually parents pay for students fees, right? That's a general case. But in some cases students are also paying for their own fees, right? That's a very specific case where the students, when the kids are like, I will also earn, I'll do side by side job, right? I'll do this and that, right? So that is a very exceptional case. Very few students you will see doing those kind of things, right? So here that student is metal carbonyl, where we know that it's a very normal thing for a ligand to donate electrons to metal by sigma bond. That's quite normal. But when the metal is like, bro, I also have electron in my d orbital, I also have the capability of donating you the electron, it starts giving back donation. So when it gives back donation, that is called as synergic bonding, and it do so by a pi bond, and it fills the which orbital of carbonyl is empty? The pi star orbital, right? So if you see, this is the pi star orbital of carbonyl which is empty, to which it is donating the electrons. Okay, so to this pi star orbital, this is donating the electrons. So electrons are always donating to pi star anti-bonding orbitals of carbonyl. Okay, that is called as synergic bonding. Acha, this all you don't have to do, you just have to know that pi star anti-bonding orbital is where the ligand is accepting the electrons. Okay, then guys, if you talk about the strength of this bonding, acha, tell me one thing. More is the electron density. You tell me, if metal has no electron in d orbital, will metal be able to back donate? Metal has no money. How metal will be able to say to his friends, let's go and do party? No, metal should have some electrons to do party, right? So if you see this metal here, this metal, if it has good electron density, then it is like, bro, I can give you my electron as well. I don't want to be under your ehsan, right? I can also give you back donation. So the condition is that these metals should have good electron density. They will be able to back donate. When the back donation is good, MC bond is very good. If this bond is very good, then this bond will be very poor. Whenever MC bond strength increases, then CO bond strength always decreases, right? And MC bond strength increases when you have electron density is high, when electron density is high on it. Okay, understood everyone? Tell me, is that clear? Is that clear? Tell me guys. Acha, now we will do some questions here. Everyone ready? Let's see. Those who are saying, ma'am, nobody asked questions from this part, ma'am. They ask you questions. JEE Mains 2022 question, which is, which of the following show minimum synergic bonding? Minimum synergic bonding. Tell me, which of the following shows minimum synergic? All you need to understand is electron density should be high. And you know one more thing. If you talk about synergic bonding in case of one metal, M3 positive will show you less, then M2 positive, then M positive. Why? Because electron density is maximum in this case. That's why synergic bonding is maximum. So if they ask you synergic bonding when there is only one metal, but the charge on the metal is different, then it will be this case. Otherwise, you will simply calculate the number of d electrons here. So if you see, here the number of d electrons is, manganese is d5, 4s1 d5. Manganese 2 means 4s1 d5, it is 2 times. So overall electron will be 5, 6, 6, 12. This overall electron will be 6. Here overall electron will be 12. Here what you will have is, if it is 12 for this, if it is 12 for two metals, then for one metal it is going to be 6. Okay. This is chromium is going to be 4s. Array, this will be 2. My bad. This is 7. This is 4s1, 3d5 for chromium, that is 6. For iron it is 4s2, 3d6, that is 8. Tell me, which one has least electron density? Electron density is minimum in this case, isn't it? Electron density is minimum in this case. Minimum electron density. If you see this, minimum electron density. So synergic bonding, that is MC bonding, will be maximum here. CO bond length will be minimum. CO bonding will be minimum here. So MC strength is maximum here. Sorry. Minimum means minimum. Ha. This is minimum means minimum. If this is minimum electron density, it is minimum, and CO will have maximum strength. So answer is C is the correct answer. Okay, right? Tell me. They are asking you minimum synergic bonding. More is the electron density, more will be the synergic bonding. Okay? Yes, everyone? Tell me. Right? Okay. Now let's talk about the synergic bonding, like the compounds that they make, the compounds. Each of these structures you should know, right? Okay. NiCO4, FeCO5, CrCO8. Then this is very important. Mn2CO10. Then you have CO2CO8. All these structures you should know, right? Okay. Now let's see how they ask you questions on these structures. If the cobalt carbonyl complex, number of CO-CO bonds is X, terminal CO is Y, then what is X plus Y? So if you see CO-CO bond, guys, if you see CO-CO bond, there is X is equals to 1. And how many terminal carbonyl you have? 1, 2, 3, 4, 5, 6. These are terminal carbonyls. These are bridged carbonyls. Okay, so here you will see that Y is equals to 6. So that's why correct answer will be 7. Okay, tell me. Clear, everyone? Yes, you told C, then very good, right? Acha, see one more thing. Before starting isomerism, one more thing I need to tell you about the EN, right? Okay? EN rule. Simple rule it is. Effective atomic number rule. Effective atomic number. See, effective atomic number is quite simple. Let's say you have a compound that is FeCO5. Now, all you have to do is, firstly, you need to calculate the electrons here, right? So, number of electrons, it is 26. Atomic number is 26 here. And this is in zero oxidation state. So, it will be 26 electrons. Plus, you have cobalt is 5 cobalts, and each cobalt is giving you 2 electrons. So, that is 36. That means it is equals to nearest noble gas, so it follows EAN. And the compounds that follows EAN, they will be more stable, right? They will be more stable. Let's see some other compound. Let's see CO, NH3 thrice, Cl3 thrice, and this is let's say it is 0. Okay, let's see. Okay, let's see this compound. Here En it follows or not. Let's see this. Here oxidation number is X plus 0 is minus 3 is equals to 0. So X is equals to plus 3. Right? So that means cobalt, which atomic number is 27. You have taken 3 electrons from here. Right? So that means this is 24. Right? And from ligands, what you have? So what you will say, the rule is to add number of electrons of cobalt plus ligands. This will give you 6. Ammonia will give you 3 into 2, that is 6. Plus chlorine will give you, each chlorine will give you 2 electrons. So 3 into 2, right? Yes. So it will be 24 plus 6 plus 6. So 36. Again it is 36. So it also follows EAN. It follows followed. Okay. So it should be equals to nearest noble gas configuration. Clear? Okay. Right. So all you have to do is calculate the number of electrons. Right. If there is zero oxidation state, so just write the atomic number. If there is some oxidation state, then subtract those many electrons and then add the ligands. Right. Okay. Done. Now last part of this is isomerism. Let's do isomerism. That is the last part. Okay. Yes. Let's do isomerism. That is the last part. Okay, Mohit. Very good. Very good, Mohit. Right? So, if you see this in isomerism, you basically have two kind of isomerism. One is structural isomerism, other is stereo. When will this end? Hi, ma'am. We are, ma'am. Done, ma'am. In next 30 minutes, it will end. Okay, just more 30 minutes more for isomerism and then we will end the class. Okay, right? Let's do. Ready, everyone? How's the Josh? Everyone in the chat box. Everyone. I think I will recover only when I leave teaching. Because the more I teach, the more this is gone. But I don't want to do that, right? So, tell me, everyone. Shall we start? Shall we start, guys? Everybody in the chat box, shall we start? How's the energy? How's the Josh? Everyone in the comment section. Everyone in the comment section. Ready. Still energy is high. Energy is high, guys. Energy is high. Yes? Okay. So, let's discuss about this. First, we talk about isomerism. So, two kind of isomerisms you have. One is structural, other is stereo. In structural isomerism, it's a very famous example, very simple example that I give to my students is isomerism is where molecular formula is same but arrangement of atom is different, right? So ma'am, what is the difference in structural and stereo? See, let's say you have a, let's say you have a plastic doll, right? A plastic body you have, plastic skeleton you have, right? You can take out the head and place it somewhere. You can take out the arm, you can take out the leg, right? But that means I can take out the arm and place it over here. I can take out the head and place it over here. That I can do with a plastic doll, right? That is structural isomerism, where I'm changing the structure only. I'm changing the linkages of the atoms, right? Stereoisomerism is where I am saying that you cannot take out the head and place it somewhere else. All I can do is I can rotate my neck like this, like this. I can take my hand like this, like this, like this. So that means in space, I am changing the arrangement. The linkages I am not changing. I'm just changing the spatial arrangement. Sometimes like this, 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 this. That is stereoisomerism, okay? Right? Now, okay. Now, once you know this is structure, this is stereoisomerism, then there are structural isomerism. There are 6 kind of structural isomerism. First is ionization, hydration, coordination, linkage, ligand, coordination, position. So these are the 6 kind of isomerisms that we have, right? So ionization isomerism is, in this case, if you see this particular coordination compound, the counter ion will be different. So if you see here, ligand is Br and counter ion is SO4. Here ligand is SO4 and the counter ion is Br. So we are interchanging those things here, right? If you see hydrate or solvate isomerism, in that case, complexes that differ in number of water molecule present as ligands, right? In hydrate molecules, number of water aqua ligands will be different. So here you have 6 aqua ligands, here you have 5 aqua ligands, right? In the case of linkage isomerism, you will have a ambidentate ligand here, right? Ambidentate ligands will be there, where the linkage with the ambidentate ligand is different. Here it is linked by nitrogen, here it is linked by oxygen, so the linkage is different, right? Then coordination isomerism is where you have two coordination spheres, right? In this case, you have cobalt with ammonia. This is chromium with CN. Now I am interchanging these things. Now ammonia is with chromium here, and here CN is with cobalt here. So that is a interchange that we can see over here. Tell me, is that clear? Right? Is that clear? Yes, students? Aditya, it definitely requires a cheat sheet. Okay, it requires, and I'll be giving you the cheat sheet because see, if you start applying the logic also you should know, but cheat sheet is important for you. So because the time is less, okay, let's be very clear. You have competition exam is also about managing the time, right? So cheat sheet is required for that, right? So ligand isomerism, if you see these things, here the ligand itself is under isomerism. So if you see the ligand itself is under the isomerism, here it's a different ligand, here it's a different ligand, but the formula of the ligand is same. And coordination position isomerism is where what you have two metals. Here in this metal, the ligand is NH3,4 and this is CONH3 twice Cl2. But in its isomer, you have CONH3 thrice Cl, and here it is different. So the ligands attached to the metal in the same complex is different. So here to this metal, different ligands attached, the attachment with different number of ligands is there, and here it is attached with different number of ligands. So the ligands are changed. It's not like their linkage is changed or this is changed. What is changed? That the arrangement of these ligands within those two metals is changed. That is called as coordination isomerism, right? Okay. Right, everyone? So, okay. Now what you have in stereoisomers, there are two categories. One is geometrical isomerism, other is optical isomerism. So geometrical isomerism in coordination number 4 is only shown by square planar, right? Tetrahedral will not show you geometrical isomerism, and optical isomerism is shown by only tetrahedral. Square planar will not show you geometrical isomerism. I'll also give you the reason behind that, right? But octahedral will show you both the things, right? So firstly, let's talk about, see, bidentate ligands, symmetrical. These are the examples of symmetrical. They are mentioned by AA or BB. Unsymmetrical ligands are these. These are unsymmetrical ligands like glycinato. So they are mentioned by AB, right? Now let's see geometrical ligands. Basically, they are cis and trans, right? So what exactly is a geometrical ligand? It is cis and trans. When they are on the same side, that is cis. When they are on the opposite side, that is trans. Okay. So we know that in tetrahedral, what is opposite to this one? This is opposite, but this is adjacent also. If this is opposite, this is... So every atom to this atom, all these atoms are adjacent, right? That means there is no opposite position. That's why cis and trans is not shown by tetrahedral. Okay. Yes. Now let's see. Yes. Now if you see coordination number 4, if you see this thing here, right, square planar complexes, there is no geometrical isomerism that we have here. These are the compounds which will never show any geometrical isomerism. I'll just show you this in square planar, right? Wait a minute. So if I see guys, if all of them are same, you can't say which is cis and which is trans. If I say one of them is changed, right? Then also I can't say which is cis. A and A are also adjacent, A and A are also opposite, right? If I say these two are same only. If I say there are bidentate ligands, let's say there are bidentate ligands which are same. These two ligands are bidentate, these are also bidentate. So you also can't tell which is cis and which is trans here. Then if you have AA and BB here, if you have two different ligands here, let's say you have this two different bidentate ligands here, right? This is first bidentate ligand, this is second bidentate ligands. So here also to this A, this B is opposite to this A, this B is also adjacent. So you can't say that which is cis and which is trans here, right? Again, not applicable. MAABB, again, this is not. So all these types are not going to show you any geometrical isomerism, right? Okay. Then for A2, B2, you will definitely see for A2, B2, right? For A2 and B2, you will definitely see. Now, if you see these are cis, if I say it like this, if I mark it like this, it will be trans. Now you will ask me, ma'am, what about A? Then ma'am, why have you not done it for AABB? See, for AABB, it was not like that. For AABB, it was like that. Tell me, if you say, ma'am, this is cis, you want trans, is there any position where you can have trans? Is there any way you can have trans? Either it can be here or it can be here. Nowhere you can have this red and red opposite to each other. That will not be square planar then, right? So that's why, right? Now if you see in A2, B2, these are next to each other, so it is cis. These are opposite to each other, so that is why it is called as trans. Okay? Then guys, we have square planar for A2BC. So here A and A are next to each other, so it is cis, and here A and A are opposite to each other, that is why it is trans isomer. Okay? Then you have ABCD, this one is quite important. Let's see this, how to answer this one, right? Let's see this, how to answer this one. If you see this here, this is, let's say this is M, this is 1, 2, 3, 4. This is A, B, C, D. Okay? Here you have to fix one atom. So in the second molecule also I am fixing this A. In the third molecule also I am fixing this A. So this is a way of understanding ABCD in case of this one, right? Okay. This I will fix, so I'll marking it that I have fixed this. Now I will interchange B and C, and it will be C and B here, and this is D. Now I will interchange D and B here. This is C and this will be B and D. Now once you have interchanged it, now you will take any of two as same. Because here bromine, here Br and Cl are from the same group, so you will take bromine and chlorine as same. Let's say here I have taken B and C as same. B and C as same. Then if B and C I have taken it as same, then can I say that Here B and C are next to each other, so this will be cis. Here B and C are next to each other, so it will be cis. Here B and C are opposite to each other, so it will be trans. So in case of ABCD, always you will have two cis and one trans. Okay, always you will have two cis and one trans isomer. Okay, right? Done. Then if you have AB2 kind of complex, if you see A and A, these are opposite, that's why they are trans. AA, that is next to each other, this is called as cis, right? Now let's talk about octahedral complexes which have any geometrical isomerism. So in this case, there is no geometrical isomerism. In all these cases, MA6, MA5P, MAB5 or MAA thrice, right? So they don't have any geometrical isomerism, but in these cases they have. If you have MA4B2, like this is the example, they are next to each other, so it is cis. They are opposite to each other, so this is trans. Simple it is, huh? If you say A3B3, in case, this is very, very important. In this case, they don't show cis and trans. They show facial and meridional isomerism. Let me show you how. Okay. See, in case of facial isomerism, what you will have, on the same face, there will be same ligands. Right? On the same face, this is the same face. This is one triangular face. Octahedral has 1, 2, 3, 4, 5, 6, 7, 8 triangular faces. On one face, when you have same ligands, that is called as facial isomerism. It is written when the ligands are written next to each other, right? And meridional is when these ligands are forming one semicircle like this. Same ligands are forming semicircle, same ligands are forming semicircle. Okay. Now how they are written? This is AA, you will leave a space, then again A. Or BB, you will leave a space, then B. That is meridional. So A3, B3 shows facial and meridional. This is very, very, very famous question, right? Then guys, we have A4BC, where if I say here, this is actually done with making some important structures here like this. If I say AA, AB and AC, this is cis, right? Where AA are next to each other. Here, if you see, A4 now you have. Here AA are next to each other and you also have BC here. So AA are also next to each other. AA are also opposite to each other, right? So this way you can't tell, but you can tell with B and C that B and C are next opposite to each other, so they are trans. Okay, right? Okay, so this is how you will tell. AA next to each other, that is cis, right? And here you will have this also AA next to each other, right? So this is how we actually tell about this one. Okay, you can actually make the structure here. If wait a minute, with structure it will help you more. Let's see, I am making A, B, and this is some C. Okay, some different compound, that is C. So we are saying that this is cis. Why? Because here A is next to A is next to A is next to A, right? All of them are next to each other, right? So this is cis. When I say you have AA and all of A over here, now according to this AA, you can't define anything. According to this AA, because their AA is also opposite to each other. AA is also next to each other, but you can define by B and C that this is trans. Okay, so this is how you do this, right? Okay, next is AA2B2, right? So in this case, when these bidentate ligands are next to each other, that is cis, this is also very important, right? Then when these are opposite to each other, they are trans. Okay. Now this is the cheat sheet that like A2B2CD will show you 6, A2BCDE will show you 9, ABCDEF will show you 15. So this is the cheat sheet of total number of geometrical isomerism, right? This is a cheat sheet again for other isomers, right? You can go through this, right? Now let's talk about optical isomers, right? Now last part of today's lecture, and here also I have made some important already I have made some important things for you here, right? See, if you want to understand about optical isomerism in detail, trust me, this is in detail if you actually want to do this. See, by seeing this lecture as well, you will be able to answer in the exam. That I can tell you. If you don't watch that lecture also, even then you will be able to answer this, because I'll be giving you direct answers here that this will show, this will not show. So this is what they are going to ask you in the exam. But if you are here for like, ma'am, I want to know, I want to see this structure, ma'am, then guys, you need to watch my lecture of isomerism. I have taken around 3 to 4 hour lecture only on coordination isomerism. It is 2 months back I have taken. If you have time, then you can go through that. But the thing that you will use in the exam will be here, right? So now whatever, if you're in class 11th, you can go through that lecture. If you're in class 12th, you are going to do JEE in next 2 months, then I would advise you just go through these sheets. Okay, so let's see this thing here, let's see this thing here. Now optical isomerism, basically it is that you will make the mirror image of that compound. If it is non-superimposable, like you have your hands, it is non-superimposable, so that is optical isomers, right? So basically in optical isomerism, what we are seeing that optical isomers should not have any plane of symmetry. Only then they will be optically active. And if you see a square planar geometry, right? Let's say I am making all my, let's say I have made all the atoms different in square planar. There will always be a plane that is cutting it into equal half, and that is this plane. That is the reason square planar will never show optical isomerism, right? They can ask you why square planar is never showing, because it will always have a plane of symmetry, right? Now these two isomers that are optical isomers of each other are also called as enantiomers, and they are of two types. One is dextro, other is levo. Dextro will rotate the plane polarized light towards right, levo will rotate it towards left, right? Okay, so they should not be superimposable with each other. Let's talk about that one by one. So first is coordination number 4. Out of this already I have written. See, again I am saying optical isomerism is all about imagination. If you see in square planar, when all of them are same, there are so many, it is not square planar, it should be tetrahedral, right? Plane of symmetry is present, optical isomerism does not exist. If 3 of them are same and 1 is different, if I say 3 of them are same and 1 is different, even then POS will be present here. If I say 2 are same and 2 are different, if 2 are same and 2 are different, if it's like this, even then plane of symmetry is present, easily plane of symmetry is present, right? But now what you will see, in this case, in the case of MABCD, when all of them are different, then POS will not be present here. Let's say if I say all of them are different, right? Okay. Okay, yes. When all of them are different, I can see plane of symmetry. If I split it like this, these are different. If I split it like this, these are different. So there will never be POS. So it is always going to show optical isomerism. If I talk about these, they are always showing plane of symmetry, so there is no optical isomerism. AB2, let's see if it is showing any POS. I'll be only talking about those compounds which are not showing any POS. Okay. Wait a minute. This is AB2. That means unsymmetrical bidentate ligands are there. So just give me a second. So if I have unsymmetrical bidentate ligands, right, no POS I need. Let's see if it is any POS is possible or not. If you see this here, right, if you see this here, right, POS is never possible. If you cut it like this, POS not possible. If you cut it like this, POS not possible. If you cut it like this, POS not possible. So nowhere any POS is possible here. So it is going to show you optical isomerism. So these two things that are going to show you optical isomerism in tetrahedral field. Then for coordination number 6, guys, what we have, I'm just going to talk about those compounds which shows you optical isomerism. You have A4. You have A4B6, right? A4 means 4 of them are same. A4B2, right? So is there any POS present here? Let's see. If I say, ouch, I think POS will exist here. Wait a minute. Let me see. If I make trans, A4 can have trans. In trans, I can say POS is existing. That is why in trans, POS exists, and that's why optical isomerism is not shown. In cis, if I say they are next to each other, in cis, this is cis. In cis, can I see any POS? No, you can't see any. Wait a minute. This is cis. If I see this in cis, cis also it is not present. Cis also, wait, I was thinking. In cis also POS is present, so optical isomerism also does not exist in cis. So they do not exist. Let's talk about in facial and meridional. This is where students usually get confused. In facial and meridional, ma'am, how POS is existing there? Let's talk about it. So if you see facial, here you can see POS is existing. This is the plane of symmetry. I can divide it into equal halves. In meridional, when they are like this, they are making a semicircle. Now in this case as well, there is a POS. I can see this over here. Directly POS is present here. I can cut it into equal halves, right? So definitely. Now here important part is that A2B2C2, A2B2C2, POS will never exist, right? In case of A3B2C, chalo, let's talk about these things, okay? A2B2C2, you have A2, you have B2, you have C2. In C2 what you have? Let's say this thing, A2B2C2. POS they are saying will never exist here. Let's see, they are next to each other, POS is not existing. Let's see, it is here. Let's see, it is here, and they are not next to each other, they are like this. Now also POS is not existing. So there is no case, if you see this here, wait a minute, E2, B2, C2. Now it depends upon which kind of structure you are talking about. If we see A2, B2, C2 in case of geometrical isomerism, wait a minute. A2, B2, C2, A2, B2, C2, 5. This is important. That there are different possibilities of A2, B2, C2. And there is one possibility where it will not exist. Okay? There is one possibility where POS, here the POS is existing. Right? Let's make all of them opposite to each other. Let's see. Let's make all of them opposite to each other. Will that exist or not? I think when they are opposite to each other, then it will not exist. Let's try to find out. Now if you cut it, now also it is existing, right? If you place it like this, if two are opposite, if all are next to each other also, let's see if all are next to each other, then it is not existing. If I say all are next to, if all are opposite, then POS is existing. Then there will be no optical isomerism. But in one case, when all of them are next to each other, right? Next to each other, then POS is not existing here. Then POS you will see will not exist here, right? So there will be non-existence of POS, but only in that case where AA, BB and CC, they are next to each other. Acha, tell me, when AA, BB, CC are next to each other, it is AB, AB, BC, CA. In this case, POS will not exist. This means this AB, BC, CA means these are the trans pairs. Okay, this means the trans pairs, right? So now if you talk about A3, B2, A3, B2, that means three of them are same. A3, B2, In this case, when you talk about trans means when two same are opposite to each other. When two same are opposite to each other, 3, 4, 5, 6, right? In this case, if you see, you can cut it into equal half easily. So in case of trans, POS is existing. If you talk about cis, if I if I say this is next to each other, this is next to each other, like this. Now can I see POS existing or not? Wait a minute. When C and C are next to each other, in this case it is not existing. Is there any chance? Any chance? Wait a minute. Here also it is different. If I place it, it is existing. I can't see it. You to can see it. If you place it like this, if you pass a POS like this, okay, it is divided into equal half. POS exists, right? So again, optical isomerism will not be shown. Then you have A, B, C, D, E, F. Now this is important. It shows you 15 GI, and all GI has optical isomerism. So total stereoisomerism is 15 plus 15 is equals to 30. Because this optical isomerism has 15 geometrical isomerism and their mirror images, right? Okay, so this is, we can't, like, this is what you have to learn as it is. Thank you, Ashwin. Thank you so much, Om Prakash, for your efforts not attending due to pre-completion of the chapter of by me. Okay, that's great, Om Prakash, that you have already done this. Right? Acha, now let's see some of the important that I want to teach you, right, individually, right? Let's see. If you talk about this thing, right, now some students feel that, ma'am, this is, ma'am, this, if you see the mirror image, ma'am, but ma'am, we can also rotate this mirror image, ma'am, then it will be superimposable, then how come it is stereoisomer? Let's see that. See, if this is X, this is Y, this is Z. This is simplest way of understanding this. Mirror image of this will be, this is Y, so this will be Y. This is Z, so this will be Z. This is X, so this will be X. You rotate it, okay? I am rotating it 1, 2, 1, 2, 3, 4, 5. I am rotating it to 180 degrees. So this X will go here, this Y will go here, this Z will go here. Okay, opposite I am doing. Now tell me, are they superimposable? X is superimposing X, Y over Z, Z over Y. The X's are not same. Their X's are not same. Then how come they are superimposable? To you it may look like superimposable, but their X's are different, right? So they are non-superimposable. Similarly with this one as well. If you see this form here, this is X, this is Y. Superimposable will be, this is X, this is Y. When you rotate it, this is cobalt, 1, 2, 3, 4, 5, 6. It will be 1, 2. This is X, this is Y, right? Okay. That is not true. What you are doing? This is X, here opposite will be X. So this will be X. This is Y, here opposite will be Y. This is Y. This is Cl, Cl. Are they superimposing? X superimposing Y? No. Y superimposing X? No. So this is non-superimposable, right? Okay. Chal. Now AA-B2C2. This is the compound. You have cis and trans. In this case, AA-B2C2. If you talk about cis, I'll just show you this here. Okay. If you talk about cis, AA, B2 means they both should be on the cis position, means like this. They should be like this. This is AA, this is B2, this is C2. So if you see this here, they have a POS or not? Yes, everyone. Cis it is. I can't find any POS over here. If I pass a POS here, or here, or here, or here, there is no symmetry over here. There is no symmetry I can see. So POS is not symmetrical, so optical isomerism is present. If you see trans, okay, trans is, any of them will be trans. Now if you divide it, like this, there is a POS that is absolutely beautiful POS that is present here, right? So that means optical isomerism will not exist here, right? Now let's do an example. Trick is, same type of ligands if you have AA, then it will be mostly optically inactive, right? More than one same pair if you have, right, like AA, AB, that will also be optically inactive. But this trick is not always applied, but yes, in most of the cases. Now this is the cheat sheet for you. Total number of geometrical isomerism, optical isomers, you can see this over here, and you can solve it yourself, right? Okay, let's do questions that they ask you, guys. Let's do some questions that they ask you, everyone. Everyone in the chat box, let's do questions that they ask you. Let's see that. The number of geometrical isomers possible is in triamine. Triamine means this is the mean, right? Trinitrite, nitro, 3-nitro, cobalt, and this is cobalt is in 3 oxidation states. So X plus 0. X is 3, this is 0, this is nitrate is -1, this is -3. So this means overall it is a neutral ligand. The number of geometrical isomers possible in this is X, and here it is Y, and here it is Y. Okay. Beta, this is A3B3. What you are thinking? Why do we even need to find? This is 2 GI. GI is 2. One is facial, other is meridional. A3B3 complex. Can you see? This is MA3B3 kind of complex. What about this one? Trioxalate chromate. This is CR. This is oxalate. Trioxalate. Right? Chromate is 3. If this is +3, this is -6. The overall charge will be -3. If I see this over here, this is chromium. 1, 2, 3, 4, 5, 6. 1, 2, 3. Is there any cis on trans that it can show? Geometrical isomerism is 0. So here it is 2, here it is 0. X is 3, Y is 0. So answer is X is 2, Y is 0. So answer is going to be 2 is the correct answer. Okay? Yes? Tell me about it. Clear? Answer is 2 is the correct answer. Okay? So, next is, let's see, this we have done, right? I'll just place it here. Right? This we have done. Next is, this is actually, I'll just write the options here. This is 1, 3, 2, and 4. That question was asked in JEE 2021. Let's see this question that is asked in JEE 2023. So this question is the total number of stereoisomers of complex. This is, okay, stereoisomers. So this is MAA to BC, right? This is M1, 2, 3, 4, 5, 6. This is AA. This is AA2, B and C. Okay, first thing is, bacha, see, these things are possible that they can give you this kind of thing. This will be cis and this will be trans. So GI will be 2, right? And we know that if you talk about here, plane of symmetry can easily pass. Here POS. Now this you have to imagine, okay? You have to start imagining that there is this square plane, and I am not using that structure because you will not get that structure in exam. You will use that. This is B and this is AB. This is, you can pass a POS here. It can easily cut it into equal half. If you have this thing, you can't pass any. If you have, this is B, this is C, this is one ligand here, one ligand here, you will not have any POS here. Not possible. So POS is not possible here. So in this case, optical isomerism will be possible. So out of this 2, optical isomerism will be 2, and total stereo isomerism is 3. 2 geometrical isomerism, and the mirror image of this will be your optical isomers, right? So that's why it is 3. Now I don't know, students get confused here. See guys, always remember, stereo isomerism is geometrical isomerism plus optical isomerism by 2. So it is 2 plus 1, that is 3. Okay, you can, if you don't not able to understand this way, 2 optical isomers are this geometrical isomer plus its mirror image. That's why we always we can't repeat this structure again and again in stereoisomer. That's why it is 3. So answer is 3 is the correct answer. Okay. Then last question of today. Acha, one thing. Acha, okay, that's bad. I was thinking to give you homework. JEE Mains 2021 question, that is, you have to tell me the isomerism. So if you talk about these two, they show you coordinate isomerism, and this can show you, this cis means it is showing you linkage isomerism is shown by this one. Solvate isomerism is shown by this one. I think optical isomerism will be shown by then this one. Okay, cis, this will show optical isomerism. So it will be A3B1C2. A3B1C2D4, that is B is the correct answer here. Okay, and we have completed it. Okay, yes everyone, tell me, is that clear? If there is any problem, then do let me know in the chat box. Right? Okay? Tell me about it, guys, if that is clear. Yes, Roshan, Rakshan, Om Prakash, Ashwin, everyone here. If there is any problem, then do let me know in the chat box. Yes, students. So this chapter is done and dusted, and that's it for today. Now I'll see you all in the next class, and tomorrow I'm starting thermodynamics and thermochemistry in the Sigma batch. I'm super excited for that. I'll see how many of you are there in the batch, and I'll see you all in the batch tomorrow at 8:30 p.m. right? So see you all tomorrow in the batch at 8:30 for thermodynamics and thermochemistry. Till then, bye bye. See you all, and write it down in the comment section. How was the lecture? Did you enjoy it or not? And whatsoever is the feedback that you feel, right? Okay then, guys, bye bye everyone, bye. Okay, bye.